Good morning, everyone, or good afternoon if you're in a different places, not like us. Welcome to the first Data Science Summer School organized by Hertie School Data Science Lab and Data and Methodology Center at the Scripps Cluster of Excellence. I would like to thank our founders, the Scripps and the Stifterverband, for their generous support that make this summer school happen. And I'm extremely happy to see you all here today, both on Zoom and in the parallel stream session on YouTube. And I would like to note a couple organizational and technical details related to this session. In the Zoom meeting, you're all muted and you have your cameras off upon entrance. Please do not unmute yourself and do not turn your cameras on unless you have a question. If you're in the Zoom meeting and you have a question, we really ask you to put the question in the chat first, but you can also raise your hand and we will allow you to speak whenever there's going to be a time for the questions to speak. But we really ask you to put the questions in the chat anyways, because that might be easier to handle the questions for our instructor. I should also remind you all that the Zoom session is being recorded. And if you're in the YouTube session for questions, you can leave them in the live chat and we will try to handle them as soon as possible. And I'm really happy to say that we are starting with our second workshop in this summer school series. This is the workshop Text as Data, Quantitative Text Analysis with R. And let me introduce you Dr. William Lowe, who is a senior research scientist at the Data Science Lab at the Hertie School. His research spans legislative politics as well as political economy, and most recently public policy, focusing on the causal inference behind estimates of racial bias in policing. And Will, the floor is yours. You can share your screen now.
Hey there. Let me go find the button. Okay, welcome everyone. This is a course on text as data. The picture you see there is from Babbage and Lovelace, a rather excellent graphic novel about the birth of the computer. I recommend that you read it. Okay, here's our plan. This broadly is going to break into 4 sessions. I'll try to keep them to about an hour each. I'm going to start by introducing text as data as a method. I'll say in the second session something about document classification. In the third, something about when documents are full of topics rather than expressing a single one or category, if we might want to call it that. And I'll end up by talking about how we might place documents and indeed words in various abstract, hopefully substantively interesting spaces. So that's our plan. Olga has already introduced me. That's very kind. I should also note that I am the emergency backup instructor. So if you were expecting a slightly different one, then now is the moment to silently slip out and no one will ever notice. I should also note that while I'm doing my thing up here, behind the curtain there, Olga is working on questions and helping out, so is Hui, and so also is Bruno. Apologies, Bruno, I didn't know you were there, but really, we love you too. They're gonna be fielding questions. Okay, some practical notes about the practical part of this course. The materials you should find as a zip file, and that's going to be available from the course page. If you download that zip file and either it unpacks itself or you unpack it, then you'll notice that each of those 4 sessions has a folder. Each of those folders is essentially an RStudio project, which means that when we're looking at the first, second, third, and fourth sessions, what you can do is simply roll over to the appropriate folder, click on the RStudio project file, and that will launch you into the right place. Inside that folder, you will find a walkthrough of a somewhat longer practical exercise, which we will do the edited highlights of. And you'll find next to it a .r file, which contains all the actual code. So if you, like me, quite like cutting and pasting, shamefully, then you can do it straight from there. Notice that you will never need to change the working directory or any of that kind of R nonsense if you're just kind of following along. Let me emphasize again that those walkthroughs are quite long, and I don't expect that we will be able to make it all the way through. But so I'm gonna hop through what I think are the essential points, but you should feel free to work through them in your own time at your own leisure. Okay. Also, notes about the slides here. This is a sliced down version of a somewhat longer talk. So if you feel like I am skipping over various bits of material, then don't panic. I know I'm doing that, but you will have the materials available to work through at whatever speed you like. So hopefully that won't be too alarming. Okay. So let's see if I can get the chat window open, and let's begin. Right, so big picture here. How can we think about text data? So I think most people are familiar with text analysis when you think about reading an op-ed or a bit of punditry, or if you're someone who likes reading grand strategy or those sorts of airport books, then sure, I mean, in some sense, that's text and it's textual analysis. We'd like to go a little bit more systematically than that. We can think about this in a number of ways. I've divided them into three here. If you are a political scientist or a sociologist, you may be more familiar with discourse analysis, a very close reading of text. We'll say a little about that. From the computer science side, we can think about this as, think about text analysis as an NLP problem, a natural language processing problem or class of problems. I will say a few things about that. We're actually not going to do either of those. We are going to treat text as data. And I want to say a few things about what that actually means. So first of all, not discourse analysis. This is an absolute block of quote, but what it's really saying is, hey, you want to do discourse analysis? You better sign up to all of our grand substantive theories about what people are trying to do in text. And what I want to say from this is that we're not going to do that. We are going to be purely a measurement kind of exercise, and not a grand theory testing kind of movement. So that's the key distinction from discourse analysis. In particular, we're not going to have any strong opinions about what your substantive theory is. We're going to try to stay just on the measurement lens, so relatively close to the data. We're also not really going to do NLP, although I think there's probably courses you can take on NLP, maybe even in the summer school, and I recommend you do them because it's a really interesting field. So again, spend just a few moments saying what it is that we're not going to do, and so you can decide how that might be useful given what we are going to do. So think about NLP as an approach to text which thinks naturally in terms of pipelines. So we have raw text, and then we're going to basically process it in various ways. We're going to segment it. We're going to turn it into tokens, figure out where the words are. We might figure out what parts of speech, whether they're nouns, whether they're adjectives, all that kind of thing. Parsing, you probably did in school, but we could also think about more formally. And sort of higher up or further down this chain, we can think about figuring out people and places and things and discerning them in raw text. And finally, extracting what we might call facts, who did what to whom. And that's an information extraction task. So if we think about this text on the right, I am reliably informed that the top part is translated by the bottom part, but I'm very willing to be corrected on that. The point I want to make there is that even finding the words in a language like Chinese is not actually trivial. That's not a small thing. So how might we go about this? Well, what our pipeline is going to generate, for example, using the tools down on the left there, Spacy is quite a good option if you're a Python person and you can get to it from R, is the kind of thing that's over on the right. So there's our named entity recognition, which is trying to pick out who the speakers are, figure out who's being talked about, and then give us a parse tree. Broadly speaking, this I think is a dependency grammar, but it's close enough. That could be super useful, but is not where we're going. Although we might very well quite like those named entities, and we might want to, for example, treat them as tokens. But that's not what we're doing. What we're doing is basically providing the measurement component for more or less any kind of social science theory. So you come with a theory. We're going to be language agnostic, which is going to be slightly alarming given the complexity of actual natural languages. And we're going to try to go as far as we can by just counting stuff, essentially tokens usually. So if discourse analysis is close reading, we're going to do distant reading, 10,000 feet, lots of texts. So advantages there is going to scale hopefully very well because we are going to be so indifferent to the linguistic features, which feels a little weird, but there it is. But we're not going to rule anything out in the sense that we might use this to find things that we might do another method, apply another method to. So here's a question. All slide collections should have Canton. There he is. So we can ask, how could this possibly work? What are the conditions for the possibility of ignoring all that linguistic stuff that I showed you that the NLP pipeline pulls out? Well, let's talk about that. Here's the big picture. For those who've met some information theory, this should actually be moderately familiar, but we're going to have a message, content, something that I'm trying to get across to you, for example, and we'll call that content. And then there's going to be the behavior, which is me waving my hands around, the stream of sound, the tokens that are being represented in it, or possibly the transcript. So we can certainly think about language doing stuff in the sense that I can threaten, I can promise, and those are actions in itself. But mostly what we're going to be thinking about here is language as kind of signaling device, as a way of getting across whatever this message is, and we're going to think about quite generic structures for the message that we get across. So again, broadly information theoretical background. We're going just to set some notation here. We're going to think about there being the message. If it's going to be continuous or proportions or something like that, I'm typically going to call it theta. Should remind you of any measurement theory classes you've taken. But sometimes the thing that we want to get across is actually something more like a topic label or something discrete, and I'm going to tend to call discrete things Z. Being British, I'm really going to call it Z, just all the way through. And the idea here is we can think about this in two directions. So here's my message, generating those words down there. That's the communication process, and then the understanding process is simply reversing this relationship. The text you see there is from Enoch Powell's career-ending speech about immigration back in the late 60s. So he's seeing the Tiber flowing with much blood because foreigners are coming to the UK or some such. But the idea here is that what we want to say is, here's the message, and the reason you see these words in this order, or at least these words, is because of the message, and that's the extraction problem. Okay. Again, notationally, there's going to be an awful lot of these things. So you may have met these directed acyclic graph type things either in a BaseNet course or in a causal inference course. So what that's trying to tell you is that there's one message and n words were generated. That's the plate. And once we know those n, they're all together trying to get at that message. So I'm going to call it Z when the message is discrete, a topic, for example, or if it's a proportion or a position, then we're going to have it theta, just like this. Okay, how do you want to read that thing if you've never read it before? You can think about this causally. I mean, we really are actually going to think about the message causing the words to happen. That's sort of natural. We can think about it statistically, which is going to be very helpful for this course because there's going to be a lot of statistical models in it. And in that case, we're thinking about a conditional probability distribution. So if we were to know what the message was, how likely are we to see this bunch of words or any word in particular? We can also think about it from a measurement perspective. This is getting a little more tendentious. We can think about the words as being independent once we know what the message is. So we're kind of saying there's signal, which is the message, and then any kind of correlation we see between individual words, the fact that one occurs more often after the other than the third, that's basically, that's due to the message or it's noise. So all of that lovely rhetorical stuff, that's noise. And practically speaking, when we look at these models, then there's going to be somewhere some parameters with these names on them, so we can go find them. I've tried to keep the notation quite close to what happens in the code, but I can't always guarantee that. Okay, so what do we have to assume about communication? This is kind of important. So these assumptions, when they fail, mean that a text-as-data approach or like a big data text analysis kind of strategy is going to fail in one or more ways. So what we need to assume is that this communication process that I described is stable, it's conventional, it's disruptible, and it's actually empirically underdetermined. Those second ones are kind of observational, like it really is disruptible, we kind of know that. But the stability and the conventionality is what we are going to rely on. So again, the question is, how do we do text as data without actually really caring about language? Well, we're going to kind of cheat a little bit and rely on the fact that what I'm going to call instrumentality and reflexivity, which sound grand, but they're not quite as exciting as that makes them out to be. And of course, we're going to do lots of probability modeling, and so randomness is going to be key. All right, let's think about convention. So what do I mean by conventional communication? Well, here's a great definition of beverage. If you've ever lived in the United States, you know that everyone loves the word beverage. It turns up all over the place. Quite strange if you're a European. They're drinks, as far as I can tell. But the key thing about beverage is, at least as asserted by this great Urban Dictionary definition, is that a beverage is a drink, but when you're not allowed to have it somewhere. So that's exactly like a nice example of the difference between X meaning Y. So if we looked up beverage in a dictionary, we would see something like liquid thing that you can consume. But actually what it really means is thing that you really shouldn't consume right here. That's X is used to mean Y. Now, we can dispute the empirical basis of that, but that's a claim about usage, which is not a claim about like word definitions or something that a dictionary or a linguist would tell you about. It's a sociological fact in some sense, if it's a fact. Okay, now that's fairly standard, right? So what I mean by reflexivity here is the people who we are going to be able to easily study with these sorts of tools are reflexive in the sense that they know that we are trying to do something like this. Politicians are the best example, hence there's going to be a lot of political examples here. This is Margaret Thatcher in 1979 saying, guys, let me tell you how you should analyze in a text as data strategy what I'm going to talk about. I am going to have 4 headings, and these are the words. It's going to be about choice, it's going to be about strength, it's going to be about renewal and opportunity. So that's kind of like laying it out, what we should count and what we should care about. Irony here is that those words don't actually occur very often, but words around them in that topic really do. So she knows that we know that she knows that she's trying to get across some things, and she's going to give us the maximum possibility. That's a somewhat subtle, or at least not coarse variety. Here's a former presidential candidate who has a much more straightforward strategy to expressing what it is that they're trying to get across. And if we kind of stare at this quote here, then after a little while and perhaps a certain amount of deep analysis, we might discover that there's some kind of theme going on, and the theme is approximately this. And so that is designed to be consumed and to be unambiguously so. Okay. If this is going to be true, in the situations where we can rely on these sorts of regularities, then we are going to, we're basically talking about institutionalized language. And what that usually means is language that happens in an institution. So random conversation in a bar, maybe not institutionalized enough. Back and forth in a court, back and forth in a legislature, maybe better in the sense that we have to understand how it is that we're going to get things across. And if that's true, then we don't have an automatic comparability solution. So we don't quite know whether the regularities in communication and understanding that happen in a legislature are in fact comparable to the ones that happen in a court or in a press conference. And so we're going to end up with quite a lot of comparability problems, which from a linguistic perspective aren't really there, but from a kind of conventional sociolinguistic perspective are. We also have quite extreme ones. If you, like me, live on a continent full of languages, then we have a kind of, these are permanently translation problems, but they occur within institutions. Okay. So we're going to rely on the stability of this relationship here, the one I drew from kind of theta to W there. So how does the content generate the words? We're going to assume they're institutionally stable. And so one question we can ask ourselves is what happens if that's not true? So here's an example of an unstable indicator of partisanship. So this is from Monroe and colleagues in a nice article called Fighting Words. And the idea there is that the y-axis there is telling you how much more is this word Iraq used by Democrats versus used by Republicans. If we were going to use it as a sign of partisanship or ideology or something that tracks those sorts of things, then this is actually kind of a terrible word. Obviously, it's a terrible word because Iraq's an actual place with things going on in it. But in this case, it signals Republicans somewhere into early 2002-3, but then all of a sudden it turns quite democratic just because Democrats are using it more often directly after that. So that means it isn't a very good sign of ideology or party ID. Now, of course, you maybe wouldn't want to use it as that, but that instability is something that's, that should worry us. In general, algorithmic stability or measurement device stability is going to be a problem. So many of you will be familiar with Google Flu Trends, which, for those of you who weren't born yet, the Google searches about flu were apparently tracking very nicely the CDC's actual measures of people with flu, and they carried on being great until they didn't. They just kind of diverged at some point. And since that was algorithmic, there's a stable relationship which Google could rely on. It didn't necessarily notice, or other people didn't notice, that it had diverged from the thing that it was measuring. So you might say this is a nice example of Goodhart's law. You'd probably be right about that. But this is the thing that we would worry about in our text analysis. We're going to track something, we're going to assume a stable relationship, and if it kind of diverges, then we're going to have to spend a lot of time in our evaluations making it clear that that didn't happen. So that's a kind of background research design concern. Okay. So that much of the text that we're going to be looking at here, or that we can look at nicely, is going to be it's going to be helpful because it wants to be used. And the extreme version of this, for example, is when I actually as a third party, give you text and say, why don't you just borrow my text? Why don't you plagiarize, please? So if we might take the ALEC organization might say, hey, here's a really great bill against anti-smoking rules. Maybe you could kind of tweak this one a little bit and have it run in your state. And then exactly that text will end up in the final text. So if you have that kind of a text analysis problem, then you're relying strongly on the fact that everybody actually wants to use the same sorts of text. And text reuse is a really good set of algorithms there. I'm going to say not much more about that because that's relatively self-contained. Okay. Lastly, I guess we are going to assume randomness here. That is to say, we are not going to go very far with deterministic algorithms. That's actually substantively reasonable, right? So we almost never say the same words twice, even if the message in our head is the same. I may have given this lecture one or more times, but it never quite comes out the same way. And I'll never get it quite as good as I did the year before last. But there it is. It's a kind of sampling process. So you're getting one sample of this particular point. So we are going to think about the variation as random, and hence a probability model or something that has some at least notional sampling concept is going to be useful. An important relativity here is that we get to decide what we're going to model and what we're going to treat as noise. And that sort of relativity is going to be very useful. Okay. It's also, I mean, you may not know this, but actually, like, people secretly, you're all Bayesians. So that probability modeling everything kind of makes sense. You may feel like you're probably not, but I'm sorry, now's the moment to tell you that's not true. Okay. So let's think about words as data. If we're going to do probability modeling, if we're going to say, all right, this is a sampling process of some kind of, if it's a sampling process of some kind of from a message, then what's the data? Yes, words as data, right? So what we do know is that the words as data, if we're going to count them, are really, really awkward. So here's an example. This is the Conservative Party manifesto in Britain from 2017 compared to its other parties. Just for the sake of argument, we're going to compare it to those things. If we think about words as dimensions or like things we could count, then it's high dimensional. It's basically nearly 4,000 words get used, word types, should we say. And that's a subset of a respectable vocabulary. It's sparse, and it's kind of key. So that's basically only about a quarter of all of the words that other parties might conceivably use. So it's already using a quite small subset of the available things it could use. And the other point here is that it's skewed. So about 1,700 of these words occurred exactly once, and so they're in some sense going to be very uninformative. And about 1,700 of them also occur. 1,700 is also the amount of times the most frequent word turned up. And that symmetry there between all of the things that occurred once and the thing that occurs most is kind of general. And that indeed is our problem. The relationship generally is the Zipf-Mandelbrot law, which says essentially if you want to know how frequent a word is, then if you were to line everybody up, all of those words up in frequency with the most frequent and the least frequent, then you would find the actual frequency to be proportional to where you are in that list. So that's if we want to think about that over on the left in raw counts, that's what you're looking at, the Conservative Party manifesto and also the corpus. And they're all kind of squished up the end because there's some super frequent things and then everything else is basically about one. Problem here is that we can't really see it. So let's log it. And now you're looking at a plausibly power relation, at least in some domains of frequency. So in log-log space, we should see these straight lines here, which is the kind of giveaway sign of Zipf's law. But the thing I want you to take away from this is that that curve for the Conservative Party manifesto does its thing. And if we look at the entire corpus, we get exactly the same structure, slightly larger. And what's not shown here is that if we cut this Conservative manifesto into, let's say, pages or chapters or sections, you would get exactly the same shape, only further down the graph. So we basically reproduce this sparseness problem at all scales, or nearly all scales. Another way to look at the same fact is that if you're reading through something and you say, have I ever met the word that I've just read before? If I didn't know any, and the answer is yes. You just keep on meeting new ones. This is the Heaps-Herdan law. So our vocabulary is just going to be, it's going to keep on growing, which is a bad situation for data analysis. Right? We don't necessarily want the things that we could possibly count to just spiral out of control this way, which is effectively what they'll do. Okay. Key things here, frequency and interestingness, basically they're inversely proportional. So there's the most, on the left there, the most frequent words, kind of boring, very frequent. There on the right, in the middle, sorry, there's the bottom of the frequency distribution, but that's mostly typos and numbers and nonsense like that, substantively uninteresting. And on the somewhere in the middle is like an interesting substantive collection of words, but gosh, that's you've got to find those guys. That's actually stuff we might care about. So the immediate thought from an NLP perspective is, oh, so the top words are kind of boring from a communication perspective. They're all sort of linguistic terms. So maybe we'll just like lop them all out. So we should be careful about that. The strategy generally is known as stop word removal, words that you should stop having in your text. And so we should take them out. There's the web is full of little lists of, hey, here are some words. Why don't you just like use those as stop words? Should be a little bit careful about that. Mostly that's an extremely strong like modeling claim. It just says this word does no work, and I just know that 100%. So maybe that's not great. We're going to look at some texts where the standard uninteresting texty words like him, her, and she are actually rather substantively interesting. So these are going to be like abortion law debates and things, and in which case he and his and her, well, that's going to do some work. So maybe we don't want to take them out. Okay. All right. So let's roll to our finish here. We've got these awkward words. What are we going to do about this broadly speaking, this data problem? Well, the first thing we're going to do is assume lots of equivalences. That is to say, sure, I see a lot of different looking words, but they're all basically the same. We did that with stop words, just said, yeah, all these ignorable. We could also bundle them together and say all of these words mean the same thing, or equivalently the same thing. Then also let's just treat them as the same word. That's a kind of a dictionary orientation. Or we could be a bit subtler, which this literature is a bit better later on, and talk about exchangeability, which I don't want to get particularly into the details here, but that's a much closer model to our story about we have this message, and then we have this this bag of things that we express, a bag of words in some sense, and that stochastically that's the relationship. Okay. So let's get ourselves a bag of words. Here's the full quote from Enoch. As I look ahead, I'm filled with foreboding, like the Roman. I seem to see the river Tiber flowing with much blood. So let's assume that, just for the sake of the slides, there are actually two documents here. We'll say more about this in a moment. First sentence, second sentence. Let's just kind of treat them as separate. So one thing we can say is, yeah, punctuation doesn't matter. So actually, my token stream on the right-hand side that's what's happening, and in both of those documents. And also case doesn't matter either. Who put case in English? Mad. Anyway, we could also assume that whenever I see a word type like I, then it always means the same thing. That's false. However, that's what we're going to do, and there are decent arguments to suggest that this is not crazy. So that I gets counted twice because assuming it means the same thing. We can also think about order and variance, and this is the kind of the tricky bit. We're just going to say it doesn't actually matter which order I said those words, which means that I can have effectively a cross table. This is a contingency table of words and documents, and this is the notorious bag of words assumption. We are actually technically going to assume that the words are exchangeable. That is to say, we imply that there's a message if we think that we can do this. Okay. So we flip that the other way around, then we end up with the kind of the baseline material that we're going to get to in the exercises, which is the document feature matrix, or the document term matrix, or the document word matrix, whatever it is that we're counting on the top, and on the rows, just the document labels. So you probably really enjoyed a categorical data analysis course sometime in the past. Well, it's time to relive those glory days. But we are actually going to be interested in models which go significantly further and differently to the ones that you saw there, because actually what we're interested in is not these counts. It's, as it were, lurking on the sidelines, the message that caused those counts to happen. And those are going to be the thetas there in gray on the right-hand side. That's actually what we're going to want. And we're going to think about the betas there, which is always going to refer in these slides to something to do with the tokens. If we're thinking about positioning, then theta and beta are positions in a space. If we're thinking about topics, then beta is how likely you would be to generate that word or token under whatever the topic distribution for the document is, and the theta will be a distribution of topics. But either way, there's going to be something kind of out there, which is going to tell us why we see what we see there. It's a latent variable problem. Okay. Two statistical assumptions, actually one statistical assumption seen both ways. So we're going to think about, we're going to be working with word rates. These are counts, can't go below 0, but can get big, as we've seen. So we're going to think about the rate at which you generate some word or some token, and we're often going to assume that's Poisson distributed, at least conditionally, on if we were to know the rate, and then the rest of the model is going to tell us what rate we should see that word happening at. So effectively, we're going to build that device on the right-hand side there. If we're in the situation that that's how words are being generated at some particular rate, more or less randomly, then, but we know that there are 100 words, or there are 5 minutes of time in a speech, which generates a certain amount of words, but can't be more if there's like a budget constraint on how many words that can be used. And we condition on that budget constraint because we think that's determined by the legislature, for example, or the fact that we can't have an infinitely long manifesto or something like that. Then we're going to condition on n, the length of the document, and then we're going to get a multinomial distribution on exactly the same assumptions. So you can think about that as being some weighted die that tells you how often you should say each of these words, given some set of probabilities, which is given by the message. And that's basically the sum total of our statistical assumptions. These are all going to be wrong, but the question is like how wrong, and do we mind? Okay. To finish up our discussion here, I want to point out two things which aren't to do with text analysis, at least not directly. We can think about not seeing things. So let's think about not seeing things. One possibility is that we just don't see a word, but that's fine because that's just a count that's 0. Another thing we might worry about is we don't see a document. So for example, we don't see a speech from this person, or we don't have a press release from this organization. And then we have a sample selection problem because we're asking ourselves, like, how did this text come about, and why don't I have text from these other people? So as I mentioned, that's 0 counts are fine because we have Poisson multinomial assumptions, and so it can be actually quite informative. However, lacking a document can be tricky. So we have to ask ourselves, what documents could we have seen but did not? Now, why would that matter? Well, let's say you're interested in polarization, then you might wonder whether a legislature was polarized, and you might want to measure it from things people say, but most people don't say anything. So depending on what their position might have been, then polarization measures from text could be all kinds of things. So if there's some systematic story about who gets to stand up and make some particular extreme or non-extreme claim, then that's going to affect our measures. So not seeing what other people would have said is in fact important. That's actually going to be generally true as a research design issue, and we should worry about it. In general, in this course, we're just going to assume that everything is kind of randomly acquired, and that's going to be false. But the solutions are not going to be in the text analysis. The solutions are going to be in the research design. Okay. From a practical perspective, I want to make one point about the terms we've been using. I talked a little bit about documents and words, but those are terms of art, and you should treat them as terms of art. So you actually get to decide what a document is. You could think documents are documents, but you could also think that they are sentences. It's a perfectly respectable text unit. They could be tweets. They could be responses in a debate. Or they could be window contexts in an embedding scenario, something like that. Like, you really do get to choose. And you get to make that choice different ways. We'll see in the examples for the topic models how it's going to be useful for statistical purposes to think of them various ways. And you also get to decide what a word is. Could be a phrase, could be a topic label even. That's why Quantitative calls them document feature matrices, because it sort of wants to be agnostic about what sorts of repeatable things we are counting. So basically, this is count data analysis of a particular flavor. Okay. Finally, we have to make a decision. What does content look like? So what structure does it have? The assumptions we're going to make here, which are by far not the only assumptions we could make, are that either we're interested in the topic that a document is trying its hardest to indicate, to tell you what it's about, or we're going to think about the document as being full of all kinds of different topics in some mixture, and we want to know what that mixture is. And finally, we're going to think that content might be positioned in some abstract, hopefully substantively interpretable space. There are network text analysis methods and various others that we won't talk about, which just make different assumptions about what content is. But those in the very stylized form are going to be our assumptions. We're just going to work through models for each of them. We also have to, once we've decided what it is that the content looks like, then we are going to have to make a decision about how we're going to model it. Because models are going to be necessary, because we can't just count the words, because there's just too many of them and they're all over the place. So we can think about the direction of modeling as discriminative or generative. For the machine learning people, this should be a fairly familiar distinction. For our purposes, we can think about it in terms of this on the right-hand side. So sometimes we actually see, or we can assume for some documents what this message actually is. Someone has maybe coded it for us. So we have visible Zs or visible thetas, or we know what the position is, we know what the topic is. And then we have a bunch of words, and we have a sample of these things, so in some sense training data. At that point, we can learn directly what the mapping is from words into our message is, and hope that's stable, and then apply it elsewhere. And that's exactly what we'll do in the second exercise. That's kind of the discriminative approach, because it's trying to distinguish messages on the basis of words directly. Often more usefully, we're going to think about generative models where we get to it indirectly. So that's Bayes' theorem on the bottom right, worth pondering if you have a small break. Ponder it some more, very useful. We're going to use it a fair amount. On the first element of the numerator that's our generation story. What is the probability you see this bunch of words given some assumption about what the content was? Maybe that content makes them very likely. Maybe that content is not the kind of thing that will generate those words. Next to it is the prior probability of the message. So some distribution over the sorts of things that people talk about in this document collection. And then the denominator just makes it all sum. Our aim is to get to the left-hand side, which is what we had directly before. So what's the distribution of possible messages? We're never going to narrow it down to exactly one, but we can kind of narrow it down a bit on the basis of seeing these words and that story about generation you see on the right. That's typically going to be an exploratory sort of model, although not always. And those are our kind of two styles. So question from the chat, does discriminative mean supervised? In this case, it does mean supervised, but in general, it means that we go for what we want directly on the assumption that it's an understanding problem. We'll see a nice example in the text classification example next, where we can actually think about going for the distribution of message. In this case, it's going to be a category topic label on the basis of words. We can do it directly and we can do it indirectly. And they're both in some sense going to be supervised, but one of them is going to try to learn how to talk and then back out the model. And the first one is just going to go for it directly. The other one is going to go for it directly. We often are going to make quite similar assumptions, but this is like a kind of a style of analysis. Yes, so the question in the chat here, confirmatory exploratory is understood like factor analysis. It's going to be understood very much like factor analysis in the final session where we think about text scaling, because that is a form of factor analysis on counts. And in that case, that's going to be fully confirmatory. That's going to be fully exploratory. And it's an open question how we can get confirmatory about that. But yes, so do you want to explore this text in general, or do you want to discern the message that you know you're going to see? And we'll see that also in the next exercise when we think about topic models and dictionary-based approaches. Those are going to be exactly the same model, but one thought of in terms of I know what I want and I'm going to go in and do it, and the other one in terms of let me explore this text and tell me what I might want. And that's the exploratory version. Great, good questions. Bing. All right. So this is Zoom. Everybody hates Zoom, or maybe you love it at this point. Introverts, yay! The fatigue version. There's kind of the bullet points I want you to take away. What might be a good idea right now is that hopefully in the background you've been pulling that zip file and unpacking it and playing around. And if you, one thing that you might do right now, I'm going to take like 1 minute break and then we'll go do the exercise, is if you see a library command at the top of the first exercise, it's going to be one intro, I think it's called. And if you don't have it installed, maybe it's a good idea to install it. We're going to use Quantitative. I also am going to use the tidyverse, and that's kind of going to be about it actually, but that's a good moment. All right. I think I'm happy to take basically a minute of questions, and then we will launch in and do something actually practical. Awesome. Everyone actually just wants to do something practical, so let's do that. All right. Okay, let's put that away.
Hey, can you hear me?
Hello, yes.
Hey, sorry, just a technical question. Where can I access the zip file?
I'm sorry, your microphone cut out just there again.
Oh, sorry. Where can I access the zip file? I haven't received anything.
According to Hui, it's on the course pages.
Okay.
And also in the chat. Right. So what you should see, if you're seeing my screen here, is this. So probably you have a significantly tidier desktop than I do, but with slightly less ridiculously named folders. But if you've unpacked, then you should see HSS text exercises. And the one we're going to be thinking about is in here, in the first intro thing. And all being well, we will, if you've got RStudio installed, then you can simply open this guy and we will have there. You'll be in the right place. And hopefully you will see these things. And we also have to hope that I haven't dropped my history in there. Otherwise you'll see all the embarrassing code that I didn't write. All right. So what I'm going to do here is walk through what you see in this intro. So if we open this intro business in a text in a browser, I'm going to put that over there. And I'm going to walk through. So you should ask. I'm trying to explain what this code does. Yeah, then we'll do that. So one note here. As I said, this is a longer section, but what are we going to do? The first thing is how do we get text into Quantitative so we can do any of this text analysis? So we are going to be in this little exercise basically practicing getting the stuff in. Then I'm going to walk through the key elements of Quantitative's understanding about how to store text. And finally, we are going to have a look at distinctive vocabulary for different groups. So a little bit like the Iraq example that you saw, just to kind of give us a sort of word county example and give you a bit of practice with Quantitative. So let's do this. I like tidyverse. Tidyverse is good. I hope you do too, because there's going to be pipes in here. Before we begin, because I'm going to forget afterwards, you may see me typing this and this together, and you'll see on my screen that turns into a little triangle because I'm one of those awful hipster ligature types. But if yours doesn't look like that, don't worry. That's just a regular recent R pipe. And if things don't work, you can always replace it with that guy. So feel free to do that as necessary. Just so you're not kind of alarmed by ligatures. It's entirely insufferable, but yeah, here we are. Okay, so let's load Quantitative. Hope that's installed. And get going. So we're here. I've put a bunch of plain text files in the data folder. You can explore them at your will. It's a bunch of manifestos from the British parliamentary election campaigns in the recent past, although not the very recent past. And I'm going to use readtext, which is a very convenient library for getting all kinds of text in. That does a lot of things, and you should feel free to explore it. But right now, we're just going to use it to read in a whole folder full of text or texts individually. And we're going to call them manifestos. Ooh, dear me. Data. Well, that's no good. Data? Ah, someone's forgotten everything. Well done, Will. All right, too late now. Awesome. I have neglected to put the texts in my zip file. That's not great. So in which case I'm going to cut straight through to the next example, which is going to be down here, and we're going to be looking at a debate about the loosening of abortion laws in the 60s, in this case, in Britain. And here I've already generated a corpus, so we're just going to pass on the corpus construction part and get here. So let's see if this works better. Fingers crossed. Yes. Okay, good. So what have I just done? Well, I skipped the first part of these things. We now have a corpus object, which is what Quantitative wants to bundle things together as. So let's do the first thing that we always do with objects in R and just summarize it. And it is called corpus bara speaker. There we are. Let's make this a bit wider. Okay. So what to take away from this? This is a bunch of, I've taken a legislative debate, pulled together all of the entries from people when they stand up and say something, bundle them together by person. And so what you're seeing here is documents aren't really documents, they're everything that this person said in this debate. And I'm going to walk briefly through what the structure of this corpus is. So our summary statistics are not the usual means and standard deviations and all that kind of thing. What we actually want to know is how long is this thing? So there's David Owen. He says 1900, he uses about 1900 tokens, but actually only 640 types of word, and apparently it's 89 sentences. He's introducing this bill, so he actually says quite a lot. Then we have here some fact about these guys, actually two facts. There's the name called speaker, and then the vote. So how did this guy actually vote when this whole debate was over? So let's have a look at this object. The key thing about a corpus object in Quantitative is that it contains two sorts of information. There's information that's actually the text and information which is facts about the documents. So facts about David Owen himself, for example, which way he voted and what his full name is and all that kind of stuff. If we want to know the facts about the document, which are actually going to be important, then we can extract them using this function here. These are document variables. Is there any possibility the text asks, can we zoom in on the text? Yes, I think I probably can zoom in on the text. Let's make all this bigger. How about, is that better? Let's hope that's better. Okay, bigger, bigger, bigger. Right, so this is docvars. We can, what are the types? So question from the chat, what are the types here? The types of words. So if I use the word constitutional, then that's a word type, and I can say constitutional, 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 and those are 3 tokens of one type. So I'm going to think about the dictionary entry tells you about types, but we're going to count tokens, so instances of that type. So if we have a look at the document variables for this, there they are, right? So that's just a data frame of the kind that you're familiar with, which has exactly the same length as the number of actual documents we've got. Now, here's a part where we should be a little bit careful. If we want to get the texts out, well, first of all, we actually don't want to get the texts out because this thing is quite small, but your thing might be much bigger. And R is going to have a hard time splurging all this text to screen. But in the unlikely event that we want it to get all the texts just as a list forgetting all of this fun information that we've got here, then we would do that. So that's how we might look at that. Okay. One of the most important things that we can do as a sort of practical terms of just like messing around with these corpus objects is we want to be able to basically slice and dice it. So we want to be able to pull out just particular speeches on the basis of these document variables. And we also sometimes want to collapse things down. So for example, we're going to look later as to, we're going to treat all the people who voted yes as essentially the same thing, collapse them into one big fat document on the assumption they're all basically exchangeable. And then analyze like a difference between yes and no kinds of speeches. And those are very, very typical kind of texty sorts of tasks we might want to do. So let's do some of them. So very first thing we're going to do here is show how we might subset this thing. So let's have a look at this. So what does that do? Gosh, that's a bit of a mess. So let's read this from left to right. So we could make a no corpus, which would be, for example, everybody in the original corpus, and then the second argument here is going to be some logical expression which picks out just the right documents on the basis of the document variables that you see there. We're not going to have to pull the document variables out ourselves. Corpus subset is going to look into the document variables and assume that that's what we're making the logical expression out of. So in this case, we could say, I want the documents where the vote turns out to be no, and also, for example, the yes question in the chat, is this in the scripts? Yes, it is just here. We're a little bit further down because I've skipped all that bit. Okay. So here we want where the votes are no, and also the number of tokens in the document as a whole is greater than 100. What does that mean? Well, it means the people who just say I, as people want to do in these sorts of debates, they don't get in there. So n tokens counts tokens. N sentence counts sentences. So if we do that, then we get a no corpus, which we can think of as exactly the same thing, just thinned down. If you think about a corpus as a data frame, you won't go too far wrong. It's trying very hard to feel like a data frame, even though it's got all this text stuffed in it. Okay, so that's so if we subset this, if we summarize this, we can see what's in this new no corp that we've made. Yeah, just these guys. So that's, okay, that's something we might want to do. We can also, and we'll do this a little bit, we'll do this in the next exercise also, using the topic models, but this is kind of neat. Actually, maybe I just want to point at this. Sometimes we might want to say, look, I don't want speakers as the unit. I want, because I saw Will's slides, and he says you can have anything as the document. So fine, I want paragraphs because they're nice and short, all that kind of thing. So one of the nice things we can do here in Quantitative, which is going to be very useful from a statistical perspective, is that we can quote reshape this corpus. And we can turn it into another unit. So we can break it down into sentences, or in this case, break it down into paragraphs. The reason we can do this is because there's a very crude way of figuring out what a paragraph is, which may not suit you. But in any case, that's what we're going to get. And the output is going to look a little bit like this, which is, so you can think about this as that document is now the first paragraph of things that David Owen said. And there's all the details about it, and that's details about him. And there's the second paragraph. So we've kind of expanded out there, but we've kept all the information. So one of the nice things about Quantitative is it's going to keep these document variables, and trundling along with whatever we construct out of them is going to keep a copy of them. So we can always kind of use them for filtering and so on. Okay. So we can, if we want, just pull out the tokens. That's actually much better than looking for just the raw text. That is to say, we can ask it to split into whatever it thinks is appropriate sets of words, things worth counting, and we'll get an object called tokens. It's going to be a list. So if, for example, we want to see the 10th element, this is the 10th document of the original thing, woo, then there we are. There's our 10th document. Now, the list content all the way up here is, gosh, that's a lot. Doobity-doobity-doobity-doo, right there. So maybe we don't want that guy. That's not very informative, but Mr. and then a punctuation is a token for all anybody knows. And those are the things that we might conceivably count. One of the primary things we're going to do is adjust this so that we don't count all of these things. It's as if some of them didn't happen. So we can do a lot with tokens in Quantitative, which are sort of potentially linguistically interesting. One thing we might want to do is bundle them together. So David Steele is clearly a person. So maybe we might actually want to say David and Steele should always be together. We might want to replace some of them with labels. We might want to remove stuff, all that kind of thing. So there's a whole bunch of tokens underscore functions here, which I won't spend very much time on, which do all kinds of stuff to tokens. We can lowercase them, we can uppercase them, we can replace them with dictionary entries, we can stem them, stuff like that. But we're just going to use those as we need them. Okay. So one thing that's a little bit further than just like counting the words. So actually, like two sort of descriptive things I want you to be able to do. The first, I guess, is to think about collocations, or can we find words which really ought to be bundled together because they're in some sense conceptually connected? And the second thing is, can we identify like the uses of words or phrases and see all of the contexts? So if we were actually going to do a slightly more qualitative analysis here, then we might want to say, how do people talk about pregnancy here? We might want to ask, okay, show me everything that everybody said about pregnancy, just with some kind of window. And that's going to be super informative from the evaluation perspective. Okay, so let's do this in two steps. I'm going to use this library here. That's also on CRAN. Feel free to install. And I'm going to use it for its collocations function. Now, if we just run this straight, we're going to need to give it tokens. So that essentially says, find me collocations, find me words which hang together more together than I would expect by chance. And I'm going to give it tokens. And that's actually going to be, honestly, like a little bit, it's going to be a bit disappointing. So these really are collocations, but these words do indeed hang together more often than chance, but there are so many of them that we can reject at any level the idea that they're separately distributed. And they're also quite boring. So I got member for, maybe that works, but this is really not what we're looking for. What we're looking for is sort of substantive phrases, people, places, all that kind of stuff. So let's do a little bit more work and meet the stop words function. So here's a bunch of stop words, things that we kind of don't want to happen in this collocations function, and there are many cases where we'll actually make use of some stop words. But there they are. What do stop words look like in English? There they are. Hopefully uninteresting. Otherwise, I'm going to have to adjust that list. Okay. So let's do this. So what we're going to do at this point is take those tokens and we're going to remove all of these stop words. But rather than kind of closing the gap, we're just going to leave a gap. So that our bigram collection, our contiguity things are messed up. See what I mean here. So that says take tokens, remove whatever's in there. If you see one, just lop it out. But also put some padding in, that is to say, leave a space, like an empty part. You'll see why we're doing this in a moment. So if we look at like the first like 20 tokens of this entry point, so that's the first element of the list of this new set of tokens, and the first 20 tokens, then we get this. So there's a gap. There's something that we removed earlier. And so when we're looking at pairs of words that go together, then nothing will connect to this guy. So now let's do that and ask for collocations of size 2. So we're just adjusting this to give it a few more arguments. It says, okay, keep the capitalization because there are people and places and English likes to capitalize, those sorts of things, and maybe they're useful. And give me 2-word phrases, hopefully. Let's have a look. So what do we got here? Well, hopefully we've got these guys. So there's a bunch of phrases that are actually interesting in this text. So if you knew nothing about this corpus, and in fact, probably this is the first time many of you have seen this corpus, then rather than reading it, one thing you really could do is walk in, do exactly this and say, aha, that's what this whole thing is about. It's about the medical profession. It's about human life. It's about abortions. It's about the Royal College of Surgeons in this case. And it's about general practitioners and risk and the Catholic Church. And you would not be wrong about that. One thing we might want to do is bundle these things together if we thought they were cool. So maybe we want to think of that as a token. Big issue here. For those of you who have a qualitative bent, you will look at these guys and say, I can't believe that I'm just counting these words separately, because clearly illegal abortions is like a conceptually coherent sort of idea. And so maybe I want to treat that as a token. And then you would go around and collect all of these things together and spend a lot of time post-processing the text so that you treat those that way. And then you would have made maybe like 100 changes in 6,000 things. And as you can imagine, any model you fit that has 6,000 things to count and you made some changes at the far end in the low frequency collection doesn't make any difference. So there's disappointment for you. For the computer science oriented folk who are actually fundamentally not interested in that kind of thing, but just want something that like scales up and does cool things, then you might also be perhaps less careful than you want to be about stop words there. So there's failure modes in both directions, but here they are. So those are our collocations. Cool. We can ask for 3-word collocations, and some of those are pretty good. I regret that the Royal Medico-Psychological Association is probably called something different at this point, but there it is. Count nested. A question in the chat says, what does count nested mean? Well, some of these phrases occur within other phrases, right? So there's a 2-word phrase inside a 3-word phrase, and how you want to deal with those things in the statistics is a question. And for some reason, Quantitative wants to tell you all about it. No idea why. You shouldn't take the statistics very seriously here. I mean, there's a log likelihood ratio, or the lambda there. But are we testing anything? No, because the models that we're assuming connected or independent's always false. So this is language, they're not actually independent. So we're just using it as a kind of a statistic, which if it's bigger, then we might say, yeah, these words are probably more together. But the test kind of irrelevant. So actually much of that stuff on the right-hand side it's just a way of sorting things. Okay, right. Other thing that we needed to be able to do was figure out how people talked about stuff. So in case you forgot to do it, let's pull out the tokens. We had that earlier. One really key object that is going to be really, it's kind of simple but useful and has interesting connections to word embeddings. Is this. This is the concordance, or the keyword in context. So we are going to ask, how do people talk about mothers in this text? First argument to keyword in context, quick. No idea why it's called that. It's kind of annoying, isn't it? Is the tokens. Second one is like something to match, and then we're going to ask for a window. So hopefully that should be fairly self-evident. We've now got something which is a left-hand side, a right-hand side, and matches for mother for everybody. And we're also going to know like who said what. So that's good. So if we have a look at the top of this thing, then that's the very top of the object. Then stretch this out a little bit. Then it says, here's Dr. John Dunwoody. He's the first person to actually say mother apparently in this thing. And that's exactly in characters where he said it. And then exactly what he said. So that was the match. And then there's a left and right example. So if you cared a lot about seeing how people used it, or you thought that mother was a really good word for some particular purpose, you would want to do this. You can also think about word embeddings as there being a mother document. And this is effectively the mother document, which we could also scale. Okay. Those are our kind of like key tools. We can collocate, find these key phrases, and we can see how things work. Okay, but actually where we were trying to go with this is to get to the document term matrix that you saw in the slides. We want documents, we want features, and then we're going to fit all our models. And that's kind of like where we often want to start. So this whole process is going is going to end up in this position. So let's make a DFM, a document feature matrix, out of those tokens. That's the simplest way to do it. We could, in fact, have like cared a bit more about those tokens, took more things out, all that kind of stuff. But for the moment, let's just count everything. And then ask ourselves, what have we got? So one thing we know is it's going to be square or rectangular, right? It's going to be a rectangular object. It's going to be 27 speakers, and there's going to be 4,039 things that we might conceivably count. Right, question in the chat. What do you mean by the idea that two-word collocations don't really change the analysis much? Well, if we saw a two-word collocation like medical association, then how often does that thing actually occur? Ballpark estimate, kind of on the order of 10 times. So we could treat that as a separate word, bundle it together, like formally treat it as a separate word. It's now something that occurred 10 times, and there are 6,000 other things, many of which occurs much more often than it. So however influential you think this is, it's got to be really, really seriously influential to make a difference against the other 5,900 of these things. That's not always true. There are sometimes like key phrases which we would mess up if we left in, but in general, people tend to be disappointed. They hope that their processing into substantively sensible things will show up in a higher quality analysis, and the more qualitative the analysis is, the more that's true, and the more kind of brute force statistically we think of, then like the less likely it is. There's a small, there used to be, looking ahead a little bit here, there used to be a small sub field of topic modeling where we tried to figure out, assign topics to multi-word phrases as well. And there's a number of very nice ways to do this. I've used one of them myself in published work. And it's cool, but it's mostly interpretable. So interpretability improves. Does the model really substantially change? Not that much, not that much. Maybe that's the model's fault. Okay. Right, so let's, we've got our DFM. We can get the words out. There's the first 40 words just there. Or we can get the document names out. Those are just useful functions for us to have. But actually what we want to do is, like, we want to be like a little bit more careful here. So here's a sequence, like the beginning of a pipeline. We're not there yet. For doing sensible things. So we'll take the corpus, and actually we're going to throw away that punctuation, and actually we're going to throw away the numbers, and we could throw away a whole bunch of other things too. And finally, we are going to actually pull out all the stop words, just so we can use tokens remove. And one thing that we learned from this is that when we do it this way, we have and we make a DFM out of it, right? So that's our new thing. It's smaller. Right? So as you might expect, still 27 documents, but actually not 4,000 things. We've thrown away a lot of word types here, and that's probably good. Okay. We can also stem them, that is to say, pull them down to their, there we are, there's ripping the ends off so that more words look similar to one another, because the ending in English has been ripped off rather abruptly. Don't do that unless you have to. And we might also think about making it even smaller because, for example, we would worry that some of these things occur only once. And how informative could a thing that occurred only once be for distinguishing speakers, of which there are 27? Well, maybe not at all. So maybe you would like to take this document term matrix and throw away anything that occurred, let's say, less than 5 times, or maybe that was said by fewer than 5 speakers. And that's what these two arguments to DFM do here. So do you want a minimum document frequency? How many speakers have to actually say this word before we're going to keep it? Or how frequent do you want it to be? Okay. So let's do this. We haven't really done any analysis. We've just sort of like, shuffled things around and like had a little bit of look. So let's compare some documents. In fact, let's do this. So often we're going to like collapse these documents in terms of their document variables. So in this case, we're going to make 3 big documents. The document for everything that everybody said, when they abstained, when they said no, and when they voted yes. Those are going to be the three things. And we can do that with this group argument. So what we're doing is adding a piece of grouping information into something which has 27 rows, but collapsing it to 3. And we're going to collapse it over all the values of vote. Okay, so that actually is going to be much smaller. Yeah, so just 3 really. Still the same number of features, but we've redefined what documents are. The people who say yes, people who say no, and people who abstain. Cool. One of the things that we quite often want to do is see like how different people, what the characteristic vocabulary is for people who are distinguished by certain document variables. So let's do that. I'm going to compare people who voted yes and people who voted no, because substantively people who abstained did so for some sort of institutional reason rather than any kind of deep facts about what they wanted. So here I'm going to subset. That works just the same way as the corpus subset. We'll take our DFM and then we'll say, look, everybody who didn't abstain, look, keep you, and then the rest is good. So now we have corpus DFM yes, no, which is just the people who said yes and just the people who said no. Cool. Okay. Yes, no, yeah, I think so. Right. So one very easy thing we can do is say, what kind of words do these people say? So let's ask what kind of things do people who object to this bill, who object to the relaxation of the abortion laws in Britain in the 60s, what kinds of words do they preferentially use? So we use this concept here, this function here is called keyness. So I'm not quite sure why it's called keyness, no idea. Perhaps Ken Benoit knows. But in this case, what we're trying to do is say, let's compare people who say no to absolutely everybody else. And in this case, everybody else is people who said yes. And find me vocabulary which is distinctive for no sorts of people. And we're going to treat all the people as essentially the same, hence bundled together. It's kind of grouping. Okay, so there's, woo, did we not make yes, no? No, we didn't. It's true. Yeah, it's true. Let's make DFM yes, no. I think we're actually going to have to make we've made the corpus, but we didn't turn it into a DFM. So fine, let's turn it into a DFM. We've got the no terms, and if we have a look at these guys, then we get a big list of all the things that no people said, right? So if you end up voting no here, then you're worried about babies and life of children and the principle of unborn things and all that kind of stuff and tragedy, right? So that's sort of saying this is distinctive vocabulary, and the way to think about that in a raw term is, here's the number of times my target, the no people, said it, and here's the number of times that the other guys said it, and so that's unbalanced. So we're seeing that like baby is a very, in some sense, very diagnostic term for saying no. It will not perhaps surprise you to know that if we do this the other way around and we ask for the distinctive yes terms, then we won't get the same ones. We will get ones that these guys like to talk about. So fine. They want to talk about social reform and termination rather than abortion and pregnancy and committees and children and women, but not actually babies. So yeah, there's some way to think about that. And finally, we might plot these things, and that's where I'm going to end. So let's actually generate a plot for these things, like a very, very simple text analysis. What do I need? I probably forgot to. Edit text plots. That looks like the right library. Boom. Okay. Right. So you're not getting anything more special than visualization here, but that is one way of saying these are the sorts of this is the kind of no language, and this is the yes language that we might be interested in. So this is a very simple group-based, frequency-oriented kind of comparison. The x-axis there is a statistic that's trying to take into account how frequent these words are anyway. and therefore how seriously we should take the fact that one side uses more than the other. Is the keenest thing, asks someone in the chat, a bit similar to LDA? It's a little bit closer to classification, actually. So if we were to know, which we do in this case, that there's yes people and there's no people, then which of these words will be really good for distinguishing between these? And one plausible answer is, well, these ones. These are the sorts of words which, if you saw, let's say, termination, then you would almost certainly bump your idea about which way this person was going to vote to the yes side. Whereas if you saw some other words, then maybe you would remain indifferent. We'll formalize that a bit in the next session. Actually, is there a best practice? Asks someone else, for making these decisions. No, try them all. The right answer with respect to, for those of you who are academics out there, is do it all the ways. And therefore the reviewer never gets to ask for doing it the other way, because we've already done it that way. That is why the appendix is yay long and the paper is yay long. Yeah. How many documents have this word? Yeah, so the statistics here are actually in hopefully trying to tell you how seriously you should take these things. So the number of documents is not going to matter very much here. In fact, we've collapsed it just down because we've just collapsed all these people who have the same, who make the same judgment together. So they're effectively one long document. But what's more important is the frequency of the word for taking it seriously. If it's very, very infrequent, it's going to be very hard to distinguish whether it's diagnostic or not. Cool. All right. We are running a little late, but that's fine, at least for me. Okay. All right, that's where I want to end here. We have to hope that my zip file construction exercises are slightly more effective in the next summary. I'll post an updated one after this whole thing is over. Okay. Let's take about a minute's break, and then we'll launch into some document classification, which is a kind of key tool for various text analysis purposes. In the meantime, of course, if you have other questions, that will also work. Thank you, person in the chat who asks what the font is. That's Minion Pro, because I'm, as I mentioned, insufferable. Adds gravitas to even people like me. Okie dokie. Well, as you may have noticed in this course, minutes are extremely short. So, oh yes, that's a question. All right, from the chat, could I recap when to use corporate tokens and DFMs? Right, and also tidiness. Okay. You think about the corpus as the standard data structure. It's like the data frame, but for text. And you should think about the tokens as being something you can extract from a corpus. And you should think about the DFM as something you could construct out of tokens. And that's kind of the sequence of events. So you want to store things in corpora. You might want to analyze text, or you might want to process what you decide to keep, and that's when you determine the tokens. That will be the point in the pipeline, as it were, that you would do that. And by the time that by the time you take all these tokens and you arrange them in this rectangular data matrix, it's kind of all over at that point, right? Then you've decided, what are my units to count? What are my documents? And what are my document variables? And that's your kind of go-to, I am now going to fit a model kind of data structure. We could do this more or less tidy. So the alternative to using quantitative might be to use something like tidy text, in which case we would think about streams of tokens and then joining to do other analyses. That's a perfectly respectable thing to do. I try it. It's really fun. It works very well for things like dictionary-based content analysis because it's naturally thought of as a join. It works slightly less well for text models that actually assume rectangular structure. So a lot of the things that we're going to look at really will expect a rectangle, which is fundamentally untidy. The tidy version of our document feature matrix would say document word, how many times it happened, and it'd be really long. But for whatever reason, perhaps historical, perhaps no good, most of our text models are going to assume something rectangular and possibly a collection of document variables. Okay, quick question here. We'll take that as the last one. Are all these things we learn unsuitable for text from Twitter for the stability requirement? So let's talk about the stability requirement. We want the relationship between the message being conveyed and, let's say, the word to be stable. One thing that used to be stable is, for example, the message you were giving and, let's say, a hashtag. But if you hijack a hashtag, then you've just disrupted it in the form that we're thinking about there. But enough people have to use it the original way for it to work. Otherwise, you've hijacked something which no longer means anything. So in this case, the stability is incomplete because there are people who are going to use this hashtag which actually want to mean something else. But actually, most people aren't using it that way. So we have like partial stability. It's kind of an interesting problem, but it's a special case of a problem that we have a lot. You can also think about the stability requirement as as something that I am going to assume when I fit all these models. Now that doesn't make it true. That just means if you believe this, then this is the model analysis that you want. So the key thing here is you can try to make it true, or as it were, work on text for which it is reasonable that is true, and obviously you should do that. But it's good to know what your assumptions are for the model, even if you know that they are also violated. For example, we're going to fit an awful lot of probability models here. We don't really believe any of them. I mean, not really, but at some point we find them useful. So that's kind of what the stability requirement is doing. You have to tell people what they need to lean on when you give them the analysis. Okay, let's launch into LDO says, yeah, sure. Is Dr. Lowe suggesting that because of the presumption that people voting yes and no will be different, it's closer to text classification? Yes, that's actually what I'm suggesting. Let me to that point, let me talk about text classification, and then I'll try to say how this keyness thing feeds in, because I think you'll find it's related. One last one, but I can't resist it. Let's do it. So about stability, is there a difference with connotations or relationship to a word understood and genuinely changing the meaning? We are going to assume that meaning is indeed unchanging over the period of time that we're looking at. So we'll see examples later where we can see it doing different work. So Iraq is the small example of that, but we can also think about longer time periods. And the longer the time period or the difference between the institutional context that it's being used in, the harder we're just going to have to lean on that stability assumption, whilst not necessarily being able to test it. So things may genuinely change meaning. It's hard to know how you estimate that, right? So we can fairly easily, if we're a computational linguist, we can just say, well, there's some betas, they're associated with tokens. There's something to do with the meaning as it's working here, but maybe we'll give them some dynamics, we'll allow them to wander around. But of course the message changes as well. So now you have two things changing, the message and also the things that you generate by the message. How exactly are you going to identify these things? Difficult question. Lots of variation, can't really tell who's who. So in some sense, the stability assumption is we kind of can't identify the message clearly unless we have very strong views about how meaning changes, or the view that it doesn't. I think that's the way I want to put that. That might scope constrain the application. All right, let's do some classification. Right. So old, stable technology. Document classification could be very useful for a couple of reasons, but the key point for us is that we are going to assume that documents have exactly one topic or one category. I'm going to just talk about those the same way. Sorry, that's unhelpful, but like from a modeling perspective, it's really the same assumption. There's going to be some Z, which is like, I am on the topic of defense. And that's all me. The entire document's all about that. That's the assumption we're going to make. We're not going to be able to test it, but we are going to make it. And the idea here is we've got a training sample where sometimes we know what the topics are. There's going to be several of them. And we've got documents in those categories. And what we want to do is directly or indirectly learn the relationship between the words and the topic indicator, and then apply it like further on. And that's actually going to be the action is where we apply it further on. So schematically, it looks a bit like this. This is from Evans et al. We'll look at that paper in more detail. If I talk about papers during these slides, then fear not, it's all in the enormous reference list at the end, so you can just look them up. In the PDF, which I will post, you should just be able to click on the name of the thing, and it will launch you into the actual paper, or as close as the darn paywalls will let you get to. Okay, so here we are. We got labeled documents. We choose some features. That's kind of what we were doing before when we were tokenizing. Right? We were saying, this, not that, maybe this. And then we're going to bung it into some kind of supervised machine learning algorithm. We don't have to be quite as glorious as that. We're actually going to be not very interested in that part. So this is not an NLP, a computer science course. It's not a machine learning course. I'm happy to give you that course, but not this one. So that's going to be basically black boxing nearly. We're going to try to pull out the simplest possible version of the text classifier. And then we're going to apply it to unlabeled documents and see how we do. And if we've got the right answer, then we should be able to assign indicators to future documents in a way that actually respects what they're about. So there's our task. Okay, cool. The two ways to think about this technology are, you could think about it as a way to, for the positive externalities, you could learn something about how the language is used, but in the process, inter alia, as it were, of fitting the text classifier. Or alternatively, you could just not care because you've got bazillions of documents and you'd really like to know what categories they're all in, what topics they're all on. And if you're in the second case, where you just don't care, then actually you're just buying yourself a research assistant, which is great, because often you are the research assistant, so who wouldn't buy themselves another one? On the first one, or in this case on the slides, what's described as the second one, we actually would like to know about those parameters because they're going to be word related as they map into the indicator. So we're going to look at two models, not because they are the state of the art, although one of them is quite close, but because they're actually easy to think about, and they provide some insight into what we're actually doing. So we're going to look at naive Bayes, which everybody starts with, and people shouldn't end with, but it's a good start. And we're going to think about this model that's going to be fundamentally a generative model, not exploratory, but generative. We're going to have an understanding model inside it. And then we're going to flip it around and treat it discriminatively, because that's actually kind of illuminating. It's going to be the same set of model assumptions, more or less, but we're going to be able to get a different discriminative model, which is actually going to be the one that you probably want to apply. And it's going to be the one that we apply in the exercises. Okay, so what are we assuming? Well, we're assuming basically this. We've got D documents. There's a big frame of D documents. Somewhere out there in the telling you about this whole document collection is how much of each topic there is in this collection. So is it 50% on defense? Who knows? But that would be theta. 50% on defense, something on something else. Let's just keep 2 actually. And then within each of those documents, then there's an indicator telling you what that particular document of N words is about. That's going to be the Z there. So Z is defense. And then there's N words. And question, how do you generate N words on defense? Well, over there's we can't roll down the list of topics. There's going to be defense and whatever the other one is. And each of them is going to have a collection of coefficients, or we'll just call them betas in this case, which tell you, okay, you want to talk about that? This is how you do it. So you want to talk about defense, use this word at a certain rate. If you want to talk about the other category, then use it at a different rate. And that's going to be, there are 2 lots of betas down there. Okay, so there's our kind of our structure. And we're going to try to learn the model about how to talk from Z to W, and then we're going to reverse it. So let's look at this. Okay, so here's the generative story. What's the probability this thing is on one of those topics? Well, who knows? It's going to be, I'm just going to call it theta here. And there's some kind of prior over it. Maybe we have an entire document collection of fitted documents. We are going to in the next couple of slides. And in fact, if it's balanced, then there's two categories, and it'll be 50-50, for example. That's fairly straightforward. That would be an easy prior. But the more interesting part is, okay, how do you generate a word? So what we're going to try to learn is this thing on the bottom. So what's the probability that I see a particular word given that I'm trying to express topic K? So I'm trying to talk about defense. And I know this is how to talk about defense. There's beta, it's sort of a dictionary about telling you what sorts of words to generate. And that gives you a probability of seeing any particular word. Might be low if you never talk about that when you're talking about defense. And we're just going to call that beta. It's going to be the interesting quantity. Okay. That's as it were, how to talk. A bit later, we're going to think about this in a discriminative mode where we're given the words and the betas, and we just try to learn that whole thing. But actually, we're going to use Bayes' theorem to get back, and we'll do that. We'll do it explicitly in a moment. Okay, so we should have an example here. So you had a debate before, and this is going to be an example way back in 2007. This is a bunch of political scientists, legal folk, thinking about affirmative action, and two cases about affirmative action with involving the University of California. And what we've got here is two cases. There's a kind of a pro and a con, a plaintiff, a respondent side to it. The California is the UC system is defending itself or defending its idea that you should have some kind of affirmative action in accepting students in both of these cases. And then there's in the background, that's just the court case, either side. But in the background, there's a whole bunch of interest groups who are writing so-called amicus briefs. That is to say, briefs that say, we really support you on whichever side you are. And here's some amazing arguments that you should probably use because we do this for a living. And hopefully, if they're successful, then those arguments turn up in the actual briefs. So the task they're interested in here is asking whether you can distinguish on the basis of a story about how to talk from the plaintiffs and the respondents themselves. Can you tell which side the amicus brief was on? Something a bit curious about this task. It's clearly sort of an instrumental task because we could just look. So what we're really trying to do when we apply this is learn something about how to talk one way or the other. And if we have a good classifier, then we will have learned how to support one side or another, which words to use more often. And so in some sense, the success of the classifier is the success of us learning how to talk in a pro-affirmative action or an anti-affirmative action way. Just to keep things clear, I'm going to call the plaintiffs the conservative side and the respondents the liberal side, and just talk about con and lib in this case. Okay. So let's go do that. So here's again our structure. We have some prior probability that any particular amicus brief is supporting the con or the lib side. And we have two labels, so we sort of know that secretly there is either this is supporting the lib side or the con side. That's going to be our Z. So our prior before we see any data, and then our quote naive part of the naive Bayes, which is in fact our bag of words assumption, says we are going to see, in this case, J word, like a whole bunch of words, or might be thousands of them. There are in fact thousands of them. And the probability that we see any particular string of words as an amicus brief, given that it's actually, for example, on the lib side, is the probability of those words given Z. And that's just going to be the product of the individual words. So all you need to know is how often you should generate this word if you're lib, or this word, or this word, or this word. We have a probability for each word, given that you're trying to express a liberal side. So that's a big product because they're all independent. That's kind of dumb in a certain sense, because Well, affirmative action is a phrase, right? So it's a bit odd to think about affirmative action being independently generated, given that you're trying to support the liberal side, because actually you generate them together. That's supposed to be the naive part. Question in the chat: what's the minimum number of documents you need for training? There is no rule of thumb, and you really shouldn't look for a rule of thumb here. One of the kind of wild things about this example is because we're generative, and only because we're in this particular quirky generative mode, in effectively building a measurement model, we actually are going to do like 4 documents, and that's insane. Like in general, we're not going to be able to do that. But here, we're not trying to go for the mapping directly, we're going to go indirectly, and so we can go word by word because of this naive assumption. Okay. So we have a prior. That's going to be 50-50 because there are 2 con cases and 2 lib cases at different periods of time, but they're both fighting the same fight, as it were. And that's going to be like 0.5. What's the probability of it being liberal? Well, it's 1 minus the probability of being conservative, which is 0.5. Great. We can just count documents and do that. And this is also fairly straightforward, right? So how do you talk that way? Well, it's pretty easy. What's the probability of seeing a word given that you're in a supportive lib brief? Well, you just count the number of words and divide by the size of the lib brief. That's almost the easiest thing you could do. So that's just a proportion. And if it's higher if it's the same for lib and con, then here's a word that's not very interesting because it doesn't distinguish between them. They're generated at the same rate. And if it does, if it's skewed, then it's probably a good word and it probably does distinguish the 2. Okay. Yeah, I'm going to return to the how many documents you need for training question in a bit. Okay, so let's generate. We've got the forward model. We know allegedly how to talk in a lib way and a con way, what sorts of words to generate, at what sorts of rates. But we want the opposite. We want to see a bunch of documents and then figure out whether we were probably con or lib. So we're going to use Bayes' theorem, and it's going to look absolutely horrendous, but we can walk through this slowly and get some intuition. So what's the probability we're looking at a liberal amicus brief, given that we have a whole bunch of words, curly brackets there, just say all the words, however many it is that you want to count. You can actually think about that as just the tokens. So like here they are as a stream, there's the tokens. Well, it's partly a function of over here, how likely we thought we were going to see a liberal amicus brief anyway. And over here, it's going to be, okay, we see the first word. How likely would that be for a liberal amicus brief to generate? Okay, how about the next one? How about the next one? And they're all independent bits of information, so they're going to get multiplied together. We're going to do the same for con and make it all sum up to 1. So those are our posterior probabilities. It's actually a little bit easier. In fact, it's going to be useful for our intuition later, not to think about the posterior probability of reading something in the lib topic, but how much more likely are you to be lib than con? So we can think about it like that. Now we have this ratio over here. That's going to be 1 when we're just not sure. And that's going to be a function of the ratio here. So if it's 50-50, then we're also not sure, and that's also 1. And here we can think about the ratio, right? So how much more likely are you to use this word if you're a liberal than a conservative is the idea. So these are all going to be multiplied together. So basically you have 50-50, you see some word, and then let's say the ratio is 10, and you're like, oh, okay, right, 10 times more likely than the number is 10. And it's much larger than 1. And so if that were the only word, then you would say, yeah, definitely liberal. Okay, that's actually not how we want to do it, because nobody can think at least I personally can't think in ratios very easily, because they're all asymmetrical, based at 0, but infinitely high the other way. And so it's kind of hard to interpret. So one thing we can do is log those ratios. And that's actually going to be kind of helpful. So for those of you who've forgotten how logs work, I know you're out there. Then what we want here is the symmetry. So if it's twice as likely to be generated by lib than con, then log 2 is 0.69. But if we flip them the other way around, it would be 0.5. And those don't look like each other, but actually they're the same proportional decrease. So that would be minus 0.69. So we have this nice symmetrical kind of interpretation. There's an interpretable 0 point. That means 50-50. You just don't know. So 0 is like, I have no idea. It's going to be really useful. some of you are looking at this and going, yeah, I kind of did all that in a stats course. Sure, you did, but there's actually deeper reasons for thinking about log ratios of probabilities here. And you might think, what could that possibly be? And the answer is psychophysics, very much based on these sorts of quantities. There's something fundamentally human brainy about thinking about log ratios of things, probably because it's an extremely good way to represent these potentially crazy quantities. So there's decision theory motivations, there's psychophysical motivations. There's actually a nice review that I've cited there. We can also think about this as the baseline for like a Barty-Terry model or a Rash model or specific measurement kind of assumptions. Lots of actual interesting substantive background for these. For our purposes, we don't care about that. What we care is that it takes a product and makes it into an addition, which allows us to say things like this. My final view about what this document's about is going to be pretty much like, okay, I have this log ratio on the right. I start, let's say 50-50 at 0. And then I literally add another piece of information to my collection that bumps me positive or negative, and then another one, and then another one. And by the time I get to the end of the document, then cool, I'm either above 0, in which case I say lib, or I'm below 0, in which case I say con. And that's our kind of like mental model about how you would read a document. Kind of dumb? Yeah, kind of dumb, but also not that dumb. All right. Quick example here, if we have a word like discriminate, then it turns out if we just do this calculation, grind through it just here, then liberals are using it about a third as much as conservatives, which means if we start at 1 and then we multiply through, then we get 3 at the end, right? So that's a real conservative word, 1/3 in this case. Okay. So the nice thing about this as a sort of side effect is that it tells us for every word, how diagnostic is it? Think keenness. So the keenness that you saw before, this is effectively keenness, or one form of keenness. So what you're learning here is if we have a look at discriminate, there's discrim, all the things that start that way, then those are the rates at which it's used, and it's preferentially a conservative word because there's 25 versus 15 of them, right? So it's preferentially used, not heavily so, not as much as prefer, but that's like a super diagnostic word for conservatives. If you see that, then you almost know that you're in one of those briefs. And the same for a bunch of other ones. And we can think about similar things from the liberal side, although they're a bit less extreme. Quick substantive thing here. None of these things are like perfectly partisan, which is kind of interesting. So there aren't like gotcha words that would never ever be used, but the rates do vary. Okay. And if we want to check, then we would actually go do a keyword in context there. So that when we looked at mothers before, here we would look at discriminate and see, is that really right? No, I think it probably is. This is the King County Bar Association. All right. Let's pause just there. That was kind of, we were doing it for the insight, as it were. But we could not do it for the insight. We could do this for real if we actually like really wanted to know how these models go. So there's the posterior probability of being liberal, and we'll take a deep breath. We'll do a small amount of algebra, which should not make you panic, and then we will see what kind of another model we could make out of all of these assumptions. So there's our original posterior probability. So let's actually just do a little bit of arranging. So we'll split it into 2 parts. We'll say, okay, there's that posterior probability. Here's a logistic function. So something that you stuff through, which is bounded at 0 and 1, and kind of looks like that. So 1/1 plus e to the minus something or other. What's the something or other? It's going to be this quantity here. So that's the log ratio you've seen before. So how much more likely are you to be a liberal amicus brief than a conservative one? And then this pile of information that we were thinking about using before. So you see the first word, it bumps you up, it bumps you down, and we sum it all up and we get to somewhere, and then we plug it into this function and we get exactly the same thing again. Question, why did we do all that? Like, what was the point of like turning the top line into the bottom line? And the answer is, with a little bit of rearranging, this will look super familiar, I think. So let's say discriminate's the word. And because we're thinking about a bag of words, we're going to see discriminate like 12 times at various points in some amicus brief. But actually they're all the same, and the order doesn't matter. So we may as well just sort of bundle them together and say, there's the import, there's the interesting thing about discriminate. That's how much more likely it is to be liberal than conservative. Let's call that beta. And then we've got 12 of them. So multiply that by 12. Same deal. We're now not walking through the tokens. We're walking through the margins of the tokens, the bottom of the DFM, should we say. What that means then is that we get this quantity at the bottom, which is, hey, logistic function, also a linear predictor, also a constant term, and then a whole bunch of like quantity that we get from data multiplied by parameter, which is exactly a logistic regression. I don't have the sound switched on, so I can't hear the deep groans at this point that like we've gone all this way and like ended up in logistic regression, but that's where we are. For reasons best known to history, the computational linguists discovered this model, they like it, and they called it maxent for reasons, yeah, who knows. Anyway, maxent. That's basically just logistic regression with some regularization, and this comes back to the comment in the chat. So let's see how this goes. But before I do that, I want to say these are the same model, right? We've actually just made the same set of assumptions, and we've just flipped our direction. Do we want to be discriminative, or do we want to be generative? Do we want to back it out via Bayes theorem, or do we want to go for Bayes theorem directly, which is what we do below. We just try to learn beta. That's just a regression problem. So it turns out there's a large number of stories about how to generate text, which have that model that you just saw, the logistic regression, as the discriminative version. So we didn't have to assume things were, we could assume they're Poisson, we could assume that they're binomial, we could assume that they were actually any kind of exponential family, and that would still be true that logistic regression will be the discriminative version of it, which is nice, because maybe we were wrong the first time. So yeah, cool. So if we want to think about the difference, it looks like this. There's naive Bayes, all the arrows telling us how to generate W. But on the other side, fundamentally the same sort of assumptions, but we're going to learn the mapping from W into the indicator. And so Z is a function of how to distinguish the categories from beta and the words over there. And eventually we might learn about the proportion of con and lib in the actual population, but individually we get a story for each document. That's our discriminative strategy. That's going to be a really good one. So if you want to take anything away from this course, then some model that's broadly speaking logit with a bunch of regularization from a DFM, it's going to take you a long way. We can get fancier on that, but it's a decent place to start. Okay, why is that much better? It really is actually much better. If you want to go classified, that's what you want, something much more like that. And the answer is because it doesn't care about a lot of things that naive Bayes cares about. So it doesn't care about all those words which don't actually discriminate the two sides, which is convenient because actually that's what you want to classify for. So if you want some intuition for this, it's quite hard to get intuition in like 6,000 dimensional spaces. So let's try it in like one space, and we're going to pretend, just for the purposes of intuition, that we're actually thinking about lib and con as being these sort of class conditional distributions, tall one, red one on the right, and the kind of wiggly one in blue on the left. And the task is, on the basis of X, tell me which one is which. If I give you X, you tell me, are you probably the one on the left or the one on the right, the blue one or the red one? If that's how they're generated, then actually all we care about is this stuff on the right. We actually only care about the boundary, which means that if we have a generative model, then we'll learn about this bump here, but we don't care because it's nowhere near the boundary. So we might learn about some feature of a linguistic quirk about the liberals, but if it's already given that they're definitely going to be a liberal amicus brief, then our discriminative model isn't going to care. It's just not going to be interested in that feature. Naive Bayes doesn't know what you can do with it, and so it tries to learn everything for all the words. So we can be a bit more efficient because we only have to care about this sort of region here, or the region of 6,000 space, which is distinguishing between the con and the lib. Okay, it is slower and hungrier. So back to the question in the chat. how many documents do you need for training? Not 4. That's way too small. So no, we're gonna need like quite a lot more documents to learn that relationship. Yeah, the convergence is going to be slower, but the model is going to be better. So if you can label more documents, then this is where it will be a good place to start. Okay. One thing I didn't say very much about in those 2 DAGs over there was there was this sort of quirky sigma thing, which is affecting beta. And the reason is you're going to have 6,000 words here. So if we think about this as a regression problem, however many documents you have, you probably don't have 6,000, which means you're going to have more variables than cases. Which in a normal situation would be game over. But in this case, what we're going to do is, well, that's just the nature of it. So what we're going to do is take all those betas, all those regression coefficients in the discriminative mode, and say, how about we either shrink them so that they act more together, and so there are effectively fewer of them, because they're tied together in some sense, outside the data. Or we say, okay, maybe there are genuinely fewer of them, and say, and I only want a certain number of these things to be non-zero, and hopefully those will pick out the vocabulary words which are super discriminative. That's the idea. So I'm describing there in a kind of very loose terms, ridge regression, L2 regularization, or lasso, L1 regularization, but that's kind of what it amounts to. In the exercise, we'll do both, because get on those doors. We're going to have some mixture of those, but either way, we've got to like pin down beta a bit, because otherwise it will fly out of control and the model won't fit. Okay, that's the downside of this one. Okay, but classification is better, bias is less, variance is a bit high, hence the regularization, and interpretation is a bit tricky, but yeah, that's fine. This is actually fairly general, right? So what we're going to do, again, in the exercises here, we'll fit both these models, or at least fit the first one. We're going to discover that it's going to be hard to interpret this second model, but it's going to be much better. So that's kind of going to be the trade-off for the rest of the day. Okay, let's pause for a couple of questions and then launch into actually doing it. I should say briefly that I didn't tell you anything about cool, fancy new machine learning technology, because in some sense, that's all detail on how the discriminative side works. Almost all of the state-of-the-art machinery is just a version of a discriminative model, which is going for a decision boundary to separate categories in whatever word space that we're, or word count space, or some function thereof that we're interested in. And so that you can make those decisions in some sense separately and on different grounds to the decisions you make about text. Hence, this is a text course, so we are focusing on what matters on the text side, but yeah, don't let me say this is what text classification looks like. This is what this is one way to do that, but in fact, in reality, you would probably want to do a few more things. In the exercises towards the end, which we almost certainly won't get to, then we can actually combine these models and get the best of both worlds, and like all kinds of ensemble tools will be very useful. But again, that's more into the machine learning end of things, and less into there's less and less text about that. And for those of you disappointed that we didn't talk about neural networks, then think about a logistic regression model and then put another one on top, and you have a neural net. I mean, you can do it fancier than that, but that's basically it. Question in the chat: besides quant text analysis, is it possible to get the meaning of text with the help of automatized summaries? Yes, I haven't said anything about text summarization, which is a sort of distinct part of computational linguistics, reasonably advanced at this point. It's actually kind of fun. Last I looked, what summarization ends up doing, at least in, like I say, last I looked, is we would like to essentially precede. So we would like to take particular sentences from a larger text in a way that makes sense, which generates an abstract, so essentially abstract writing. And so then the criteria for like how they hang together and all that kind of thing is a kind of separate issue. But yeah, there's models for that. Right, important question in the chat here. Actually, two, yeah. So by regularization, I mean, regardless of what's in the text, I have a bunch of parameters in this model. In this case, they're beta. They're literally like regression coefficients. But there are too many of them, and if they fit the data, they'll overfit it. They will just learn it basically, and then the model will break. If you've ever broken a logistic regression, it's kind of easy. So in this case, you will break it because you'll have perfect separation, because in 6,000 dimensions, you can separate almost anything, particularly less than 6,000 objects. So the regularization just says, I know that it looks like I should have 6,000 betas, but actually I want effectively like 3 or 4 or just a smaller number. And so I can make it feel like there are a smaller number by forcing them to have similar values to each other. Typically, I'll shrink them towards something. So I can either do that, that's ridge regression. So I force them to move with each other, and so the degrees of freedom are smaller. Or alternatively, I can selectively ask to switch them off when they don't seem to be doing any work, like actually set them to 0, not by maximum likelihood in the simple sense, but like force them to many of them to be actually strictly 0. And so I will have fewer. Both of those are forms of regularization in the sense that they're constraining a large number of parameters to behave like they're a smaller number. Other good question in the chat, when I say a document has one topic, does that mean it must be binary in nature? No, that's important. So there are two things. You can be con or lib. Let's take the British manifesto example. In the US, you can be Republican or Democrat, but in the UK, you can, for example, be Labour, Conservative, or Liberal Democrat. If the task is to distinguish manifestos, then when I say a document has one topic indicator, in the British case, that means it's either Conservative or Labour or Liberal Democrat. So 3 is fine, but the point is bits of the text aren't different topics. The whole thing is assumed to be all Liberal Democrat or all Conservative or all Labour. That's the key thing for our text analysis, for our text classification. In the next session, we'll see where that's not true, and there are all kinds of topics all over the place. Alrighty, let's go do some practical things and hope that I've filled my zip file more successfully. Here. Yeah, I think it's freestanding, so let's hope for the best. Boom. Okay. So if I remember correctly, we don't actually need any data because it's built into one of these. So we'll do the same old things again. Probably won't get to that bottom bit. Right. Tidyverse, Quantitative. Again, you probably had Quantitative, but you and text models. I'm just starting from scratch because why not? Okay. So what I want to do is grab a simple, example of like a classification problem. It's not going to be a particularly social science interesting one, although the data scientists care a lot about this in the industrial contexts. This is just going to be movie reviews, pretty classic kind of data set. Do you love this movie? Do you like it? Do you not like it? That actually is, you should probably think about it as at least ordinal, maybe even continuous, but in our case, it's just going to be positive and negative. You can also think about this as secretly doing sentiment analysis. So if you came for sentiment analysis, this is one like fairly standard way to do sentiment analysis. There are simpler ones, but this will be the kind of go-to method if you want to do that. Okay, so what are we going to do here? Let's have a look at the document variables associated with this. Right, so we have the sentiment, neg, pos in this case, and then a bunch of IDs for the actual the actual things. No idea what they're like. So we're not gonna need them particularly. All right, so just now you should be very careful here. Don't type as character corp movies and then hit return. Otherwise your RStudio will lock up for a while because there's an awful lot of these things. About 2,000, I think, which is an awful lot for RStudio showing you on the screen. We're just going to have a look at the 507th, and the reason this is chosen is because it's short. Okay, so here's a review of the kind of movie I'd make. It's extraordinarily horrendous, and I'm not going to waste any words on it. That's the end of the review. Okay. Let's see. So one of the things that we're going to end up doing here is we're going to do a bit of work because we've got to separate a training set, which we have the right answers as to whether it's a negative or a positive review, and a test set, which actually we know the answers, but we're going to like pretend that we don't, so that we could see how it would work on cases where we don't know the right answer. In reality, we really won't know the right answer. In this case, we can actually check, so we can see how well we fit in sample and how well we fit out of sample. Yeah, there it is. So a little bit of exercise here. We're just going to like break up our corpora into training and test, more or less randomly. Notice I set the seed here, so hopefully you'll get the same random numbers. Never can tell with R, but probably will. And then we'll get two corpora training test. We'll make them line up, and then we'll be off. And the actual kind of fitting this classifier as a model is going to be very, should we say, underwhelming, right? It's just going to kind of happen, and that's that. So let's do this. So I'm going to, just for convenience, add an ID here, and then use that ID to sample. So I really don't want to spend like too much time on this, because in real cases you wouldn't necessarily do it. So we set the seed. The training ones are going to be 500 from the negative and 500 from the positive, randomly sampled. And then the test ones are going to be everything else. That's what our set diff does there. Of all the numbers of 0 to 2,000, give me the ones that aren't in ID train. That's what set diff does. Very useful thing, set diff. Should figure out that function. But for our purposes, yeah, sure, we'll just make two corpora. So I'm going to take corp movies is the corpus, and we're going to say if your ID, your numeric ID that I just added, is in the training collection, keep me, and otherwise don't. And then the exact opposite for test corp. So if your ID numeric is one of the ID tests, then keep me. The in there, also very useful function. What means is the thing, for each thing on the left, is it in the collection of things on the right? Okay. So I'm going to pass on that part. Right. Okay. So two things. We are going to, data file, yes, no, that's fine. In the chat, you're saying, hey, there's nothing in the data file. That's okay. If you load this library, you will find magically that it is available. So yeah, do that, leap into the blue, and you will discover that it's actually built into the package. Which is apologies for giving you a data folder that's empty, but that's not helpful. But if you follow along on the code, this will actually go. Okay. The test and train sets are indeed assuming that the frequency of pos and negs are the same. Quick question on that. How would so good question. How would we deal with imbalance? So let's if we can build some intuition here as follows. Our training set is balanced, but maybe in the real world there are a lot more negative reviews. I don't know whether that's true. I don't really read movie reviews. Probably accounts for such terrible movies I watch. And the mismatch between those may be kind of problematic. But one thing I should note here is if you're using a kind of classifier which has an intercept in it, for example, this regularized logistic regression thing, which is what we talked about last on the slides and what we're about to apply right now, then you'll notice that we have an interpretation for the intercept, which is a priori, like how likely are you to see, let's say, a pos or a negative term. That's actually what that intercept is going to mean. So one kind of cute thing you can do with these particular models, and not necessarily all of them, but like that one in particular, is that's going to be learnt on the basis of the training set. And so it's going to be presumably 50-50. But if the real, so you can fit that model, and if the real balance is actually much more negative, then one thing cutely you can do is walk in and then just adjust it up or down, because it's changing the prior probability of seeing a negative review. We just make it more likely. So just bump it up a bit, and we can do that algorithmically. And that will correct all the output probabilities for the new distribution that you think is not the same. If you don't know what it is, then you're kind of in a bit of trouble. The other thing you can do is take the probabilities at the end of the classifier. We're going to get probability that you're negative and probability that you're positive, right? So that's going to be the output. Then you can always use Bayes' theorem and like reweight according to the population proportions at that point. So we don't have to delve into the model. That's another way to get rid of the imbalance problem. Basically get the probabilities and then bump them up or down appropriately with Bayes' theorem. Okay. But right now we'll keep it like nice and simple. Okay. So the two things we're going to do, we're going to make a training corpus, we'll make a test corpus, we're going to do this thing, we are going to evaluate this model a little bit, and then we're all going to go for lunch or whatever it is around your way. But let's do this first. So here's us in one long pipe, and here pipes promised. I promised there were pipes. There were pipes. So we're going to take these tokens from the training corpus. We're going to remove the punctuation. We're going to remove the symbols, the numbers, URLs, all that kind of nonsense. And that's us piping it into taking out a whole bunch of stop words, because we're just going to do that. Live dangerously. And we're going to put it all to lowercase. And we are going to put the whole thing into a DFM. So we get a rectangular documents by newly no stop words, like countable words in there, all in lowercase. Fine. And then to make this thing go, we're going to make sure that we don't have like too many low frequency things in here. So we're just going to lop out everything, any one of these columns that occurs less than 5 times altogether. And that's going to get us a rectangular training data set. Great, there it is. It takes a moment because there's quite a lot of text here, but it's reasonably quick. Right. Question in the chat. Why have we got training and test? Well, we are going to train this thing. That is to say, we're going to try to learn the mapping from the message, which is the topic here, into the words, or strictly speaking, the words into the message. We're going to learn that mapping on the basis of knowing both sides sometimes. That's the training set, because we actually observe whether it's negative or positive for a whole bunch of documents. And that's cool. That just asks us like whether we can learn this relationship, but it's not going to do us any good, because we had those labels in advance. So why are we fitting a classifier? We don't actually care. In this case, we're not going to care about any of the coefficients or anything like that. We just want a good classifier. But yeah, knowing the answer is not very helpful. It just doesn't work for no reason. What we'd like to do is apply it to new stuff. So our test set is going to be cases where we happen in this particular case to know the answer, but in general, we're going to see how well would we do if we didn't. So we're going to generalize to the new test set. And in general, we're not going to do as well, right? That's kind of obvious. But the question is, how much worse do we do when we try to generalize to this new test set? We know it comes from the same distribution as the training set, because I just randomly chose them all from it. But that's going to be a measure of like quality, because it's going to tell us in real life, if we actually applied it to stuff we didn't know the categories of, how well can we expect to do? Hope that makes sense. Yeah, we'll actually compare in evaluation, we'll compare how well we do on training and how well we do on test. And so you can see that these are actually kind of different, and why one is more important. Okay. So let's make a test set, and that actually goes kind of the same way, with one significant quirk, which you shouldn't forget. So here we are all again, all the same stuff, keeps on going, and we do a bit less stuff here, because for the test set, all we actually need to do is make sure that for everything that we counted in the training set, there's a column for it over in the test set, right? So if we're going to have coefficients, we're going to have something to multiply them by. And so one of the things that you are probably not used to, if you're like used to regression kind of problems, is suddenly discovering that your generalization data just doesn't have measurements over here, and you can't do anything, right? So if you don't have a covariate, what exactly would you multiply that coefficient by? So we're going to make sure that's true. And so for example, if a word doesn't occur in the training set, then but it does over here, then we're just going to ignore it in the test set, because what can we know about that word? Conversely, if a word does occur in the training set, but for accidental reasons never in the test set, and zip means that's going to happen, then we better make sure we got a kind of a placeholder for it. We just set it to 0 over in the test set, because we're going to have something. Okay, so how do we do that? That would be really boring to program. So what we're going to do is use this function here, DFM match. So we're going to take the feature names, the names of the word types, from the training set and say, make this DFM that I've just created kind of like that. Make sure it all lines up, add zeros as necessary. If you don't do that, it's not going to go so well. Woo. There. Okay. That also takes a moment. All right, we'll fit the model. And this is where disappointment sets in. There's kind of nothing much going on. Well, everything is happening under the hood. This is a GLMNet model, so we're going to have a mixture, as I mentioned, of lasso and ridge regression, so-called elastic net. And that's not going to really exercise us very much here, because we're going to treat it more or less like a black box. It's going to have input data, which is going to be the first argument, train DFM, and something to train it on, that is to say, the right answers. And so we're now going to pull out of the document variables the sentiment, the neg-pos column. That's what that $sign is doing there, pretending the DFM is kind of actually like a data frame, which kind of works. So there's X's and Y's essentially, and we'll fit that model. Okay. Right, what do we get out of this model? Look at this. Always summarize. So we called this thing, there's the X, there's the Y. The lambda there is actually how important each of these sources of regularization should be, because we're going to learn some convex combination of them. It's not really going to exercise us very much here. Mostly what this model is going to do is throw away words. So you can see what's described here is estimated feature scores. You can think about as regression coefficients. And what it says is basically, if you, for example, see the word plot, then you should make the chance of being positive like slightly negative for whatever reason. Okay, but if you see these sorts of words over here, church parties and so on, these will have no effect at all. We just like set those coefficients to 0. So it's as if we never read those words. So that's what I mean by regularization. Actually, only a few of these coefficients are going to be non-zero. They're just the ones close to the boundary of neg and pos, ideally. Okay, so that's what that thing looks like. It's going to be really quite hard to go peer these regression coefficients. So I'm actually going to skip that part because it's in some sense quite boring. What I do want to point out is that there's a little bit of code here, which I recommend you have a look at. That's me pulling it out and then sorting them. So basically, in the crudest sense, what are the words that would really make you think it's more likely to be positive versus more likely to be negative? So it turns out that these are those words, right? So we apparently... Apparently those are positive words. Well, one thing I learned about movie reviews is that, first of all, horrific means it's a great movie. And second of all, that Pantaleano is a word, and I don't know what that word means. Maybe one of you will tell me what it means. But on the other side, then those are the words which actually are saying, no, this movie is terrible. And there aren't so many of them, but that's the extreme one. Okay, right. The important thing about this from a text point of view is actually like what the output looks like. How well do we do? Because we can tweak the black box, make a different choice, all that kind of stuff. That's all fine. But let's actually see how this thing will go in practice. So one thing that we're going to get out is we're going to have a look at the predictions. We can think about predictions two ways. So any of these models have it. So the training model has a view about, for each of the things that it really knew the answer to, how likely could it make it? And it won't be 0 or 1, it'll be somewhere in the middle because it's trying to learn a general relationship. But then those are either the predictions will be either the probabilities, or if we ask directly for a prediction and don't ask for the probabilities, then it will just pick the one that's kind of, if it's greater than 0.5, it'll pick one. If it's less than 0.5, it'll pick the other one because there are two categories. Or it'll pick the largest probability category if there are multiple categories. So here's that case. So we'll have a look at training predictions. So what do these training predictions look like? We'll just have a look at the top. Should look exactly what you expect, right? We think, oh, well, we kind of know that all the first ones should be negative, and this is getting them all right. So negative, 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 and so on. Yeah, no surprise there. What's interesting to us more is how well do we do? So how do we tell how well do we do? Well, what we're going to do is line up the right answers and what this model thought the answers were, and then cross-tabulate them. So it's actually just going to be one very simple table command. So the model is, there's what the model thinks each case was, and there's the true one, which is, quote, the right answer from the original data, and there's the cross table. So then take away from that is basically everything on the diagonal is getting it right, and everything in the off diagonal is a particular kind of mistake. So this is a very simple case where there's only two categories, but actually you could have loads, right? So if there's like 20 of these things, then there's going to be some complicated structure of what you tend to mistake for what. Question in the chat, what's the sentiment dictionary used here? None at all. So we're trying to learn the sentiment dictionary in a certain way. So this is the idea that we have sentiment tagged reviews, which you don't always have, but like, let's assume that we actually have them tagged. The output, the outcome, the indicator is pos and neg in this case. And then we actually want to learn the dictionary. So in some sense, the dictionary, there isn't really a dictionary, but the dictionary contains the word plot and the word life, and it doesn't contain drink or drive. In the sense that if you want to know why it makes the decisions it makes, then knowing how often drink or drive turns up in this text data is irrelevant. So it's kind of learning its own in a certain sense. You can not learn that, right? So you can say, I have a whole like dictionary full of sentiment terms, pos and neg. There are plenty of those around. Quantitative sentiment has a bunch of them. And in that case, what you're saying is, I know better than this, or I don't have any labeled data to learn the relationship, so I'm just going to assert it. And then I just count whatever words I've got. So here we're trying to get around that and try to say, no, I want to learn what a sentiment dictionary for movie reviews would look like. Okay, so here's our evaluation, right? So 494 cases that were negative were in fact established. The model correctly said they were negative. But 6 of them were in fact positive. But those diagonal things are kind of interesting, but we're also in sample here, so we should expect it to be good. But what we can do is then ask how do we look out of sample? So we'll make some predictions from the test set, and then compare the test predictions to the test sentiment. Right? So then when we do our table, that's not so great, right? So there was apparently things that got learned in the training data that are wrong for the test data. So there's 89 errors where said it was positive, but in fact it was negative. Okay, in the chat, what about? Yep. Yes, that is correct. So this is assuming that at least some of the documents are, we've added a label to them. We would have to do that ourselves. Yes, that's true, because we're trying to learn it directly. This is not exploratory. We know what the relationship is. We have a few examples of it. We need to generalize it. That's what's happening there. Yes, the non-zero words are the only ones that this model has decided are worth keeping. Can you assign scores to documents rather than binary? In text classification, no. But then you have a regression problem. So, which is like a regular regression problem with let's say an ordinal or a normally distributed outcome variable. Similar things apply. So you won't get much help from a text package if you want to treat the message there as being something ordinal or something integral, like an actual sentiment level. But you can do all the things to the text and simply change the nature of the output variable and flip into, for example, glmnet, which is what's happening underneath anyway, which is a much more general regression package. So yeah, you could feel free to do that. In fact, that's a perfectly other good way to do sentiment analysis if that were actually what you want to do. Key thing about this model is that it doesn't actually know that pos is pos and neg is neg. They're just categories. And the only question is how to tell them apart. Can we learn a general way to tell them apart? Yeah. What did I do with the test-conf command? The test-conf command isn't really a command. It's simply this table here. Yeah, so I was just giving the table a name and then like saying its name, and then up comes the table. So it's simply the cross table of test predictions and sentiment. The reason I'm giving these tables a name is because we're not done with them yet. It's actually we're going to need them for other stuff. In particular, we're going to need them for two things. What we actually tend to want to know is more to do with precision and recall, which are different error measures. And so one of the most important things that every field essentially reinvents is this precision recall distinction when we have a prediction. If you think about algorithmic fairness or any of these other things, all of these quantities that get talked about are essentially precision recall or calibration, which we'll look at later. So let's, what do we mean here? So let's just do it, and then I'll say something about it. So let's take that test conference table, this one here, this table, and make the rows sum to 1. So what does that mean? Well, it means we want to know of all of the negative, of all of the cases that the model said was negative, what proportion of them were actually negative? Notice this is a different question to, of all the actually negative reviews, which of them did the model say was negative? These are opposite conditional probabilities, but you may want to pause a moment and be clear in your head that these are different. They may be numerically somewhat similar, but they're really different quantities. So this one, how much should I trust my model, is a precision question, because we're saying model says this, were they right? Not here's the thing that this model should find, did it? That's a recall question. But we can get that by doing this. Right, so we have the precision, right, for negative cases, for things that the model said were negative, is about 80%, and about 79% for the positive cases, which is a useful thing to know. Two things make this a useful thing to know. First of all, do I trust my model? Answer is that much. Maybe, maybe not. Is 80% good enough? Who knows? What are you missing? Good question. These are often different by category. So some categories are just harder to distinguish from others. So if you have multiple ones, then you may have quite low precision and recall for them. We can, of course, do this the other way and ask the question, what about recall? So if it's actually negative, how likely is this model to actually know that? And weirdly, numerically, like a little bit, not quite the same, but fairly similar, right? So now we sum to 1 vertically. So we're thinking of all of these actually negative cases, 79% of them were actually negative, and 82 of the positive cases were actually positive, and the rest were kind of errors, right? So that's recall. Again, numerically similar, but different questions. For social science applications, one of these may be wildly more important than the other one. That is to say, you may want to be very, very sure that you have a tool which gives you what it says it's giving you, and then you care about precision. Or you may be super interested in making sure that you capture all of the things that you're trying to capture with your model, and you don't mind like false positives all over the place, in which case you're recall heavy. And the tricky thing here is that they trade off, right? So you can make the recall a lot higher, but at the expense of false positives, that is to say lower precision, and you can make the precision higher, but at the expense of missing some stuff, that is to say low recall. That is a generally useful way to think about pretty much all of our text tools. Okay. Right. One thing I actually want to end with this guy. I think I'll skip the rest of it, but this is important. I just assumed that that this model was willing to give us like a flat out prediction, but actually what it gives us is probabilities. So what's the probability that it's negative rather than that? So one of the things we can do is ask what sorts of probabilities does this thing generate? So here's some test probabilities. Notice we're asking for a prediction, we're using the test data. I mean, we did this before, but we're adding the type probability. So we don't just want the prediction, we want the actual numerical thing. So what we get, there's test probabilities. They come in a matrix because that's the way I did it way back in the day. But we'll do that. We'll put them in a data frame. Let's do that because data frames are nice. And have a look. And then there's some questions in the chat that I should answer. Okay, let's take a quick look at these, and then we'll see what the chat does. Right. So just there's a pretty standard output for a classifier. So there's the document, and we apparently think it's actually 78% chance to be negative. So if we had a threshold of 0.5, we definitely bump negative. If we had a threshold of 0.8 because we want to be sure, maybe we'd leave it out, or maybe we'd say positive because we thought that one of these errors, mistaking precision or bad recall or bad precision, was in fact worse than the other one. If we had a loss function, we'd trade them off. Let's see what's happening in the chat. Yes, precision and recall is exactly specificity and sensitivity. It's also type 1, type 2 error, producer error, consumer error if you're a remote sensing person, sins of omission, sins of commission if you're a theological person. Everybody reinvents that distinction. False positives, like true positives, like all that kind of stuff. You go to here and you find a very large table devoted to all the ways that you can label the parts of, say, 2 by 2 and margins under confusion matrix, probably, because what I showed you there before I did all the normalization on the rows and things is essentially a confusion matrix. Where like truth is on one side and the prediction is on the other, and then we're worrying about like how much is in which bit. Yeah, so it's all the same. Did we normalize and center the data frame? We did not. We didn't do any darn thing at all, which is kind of surprising. We could probably do better if we did those. There's all kinds of pre-processing we could do to that DFM, and indeed Quantitative will give you various ways to do that. We just didn't because, in some sense, that's detail. Feel free to do it and see whether you do better or worse or something in between. The data pre-processing is useful, usually helpful. This is what you're seeing in the examples here is in no way like actually how you should do it. This is kind of the edited highlights. There are lots of exploratory steps in the middle and like testing things out and dead ends and all that kind of stuff. But gosh, didn't want to give you all those. So this is just like exercise the very basic tools and like hit the high points of the evaluation, which are basically precision, recall, and calibration, which we'll talk about right now. Okay. So the plot here, I'm not going to make the plot, but because you can see it, is what sorts of probabilities are these? So can have a look at the positive ones. This is the number in this column here. So what sorts of certainty do we have? This model is apparently not always particularly certain. Right? So it rather seldom, these are the possible probabilities it could give you, obviously from 0 to 1. So it's seldom that sure, probability 1, of something being positive, and it's seldom sure that something's negative. And there's a whole pile of cases where, here's around 50-50, right? So there is a region where this model is fundamentally uncertain. We couldn't see that from the previous checks where we just cross-tabulated them because we had to plump one way or the other. We had to jump negative or jump positive. But actually, we got more information than that in here. So one thing, the little exercise that you see here is where we say, all right, maybe, and this is a perfectly reasonable like application here, maybe we have this tool, but we only want to actually, we only want action to happen when we're sure enough, when this probability is like, let's say over 0.8 in one direction or another. And that's what this exercise is doing here. So if we take all those predictions and say, look, I don't trust you when you're like really on like 0.5 kind of things. That just says you're very uncertain. And so we'll withhold any judgment there. We'll actually won't classify at that point. We'll simply take the probability as an interesting fact and then step back and do something else. So if we leave out those uncertain ones, then one thing that's pretty clear is that our test results get better. So there's the output there, because apparently this model is fairly reasonable. And its uncertainty is in some sense quite reflective of an appropriate ambiguity about the review. So yeah, we can make the neg and pos diagonal here quite a bit bigger. You'll notice that the overall numbers here are way down. That's because it's using about 40%, because there's only about 40% where it's certain enough that we were willing to take it seriously. It's just the edge bits there. On the other hand, if we do like pull down to just where this model is respectably certain, then we can make our recall and precision really quite high, so like 95% or so. That's what you're looking at down there. So one thing that that's kind of important here, both for the classification literature, but also for like the algorithmic bias literature and like any like machine learning or data science application of something that classifies stuff, is not just precision and recall, but it's calibration. So question, what's calibration? A classifier, by which I mean this guy, but also I mean a person who can tell you how sure they are about something, is in fact appropriately uncertain. So when we ask whether a classifier of any kind is calibrated, we're not asking how good are you at making the final decision. We're asking when things are ambiguous, are you appropriately uncertain? So are you overconfident or underconfident? And ideally, you should be just confident enough. So what does that mean? Well, it means that if you're a classifier and you say the probability of this being positive is 0.7, then one implication of that is that if we take all of the things you said were probability 0.7 of being positive, and then we go look, then 70% of them should be positive. Then you're appropriately calibrated. Question in the chat, precision or regression. So true positives are recall, and true positives, they're both precision. Right? So the true positive, false positive thing always confuses me. I would much more happily think about it in probability terms. So on the recall side, what proportion of the really negative ones do you get right? That's recall. And of the things that this model says are negative, how many of them are? And that's precision. So precision is how seriously you should take the thing, and recall is in some sense a sometimes unknowable fact about whether you're getting all the right answers. It's sometimes unknowable because you can't check, in the sense that you would need to know all of the right answers. So recall is harder. Sometimes you think about recall as coverage. Like how many of those cases did you actually get? Okay, so calibration here, we're going to look at all the 0.7s, or in a bin somewhere around 0.7, somewhere around 0.8, somewhere around 0.9 for all of these bins, and then ask, are you appropriately uncertain? So do the actual, as it turns out, this is partly a precision measure, does that turn out to be about right? Are 70% of the things you say 0.7 negative? Are they in fact negative? If you are, you're calibrated, which is pretty cool, because we might use that probability for something, for example, chopping out the uncertain bits. So what you're looking at down here is this horrendous piece of code here, but all that's actually happening is that I'm taking all of these guys and bundling them into bins of size 0.1. And what we get is this output here. So there's the bin that has, the middle of the bin is 0.05, so it goes from 0 to 0.1. Like those are all the predictions that you made. And then there's the proportion of time they actually were that thing, where you were correct. And then we get that. So if we visualize this, right, and if this classifier were perfectly calibrated, if it were uncertain exactly where it needed to be uncertain, then so here's what it predicts, and here's the actual proportions, then we will be right along this line here. We're actually a little bit overconfident, right? So our predicted probability is a little bit higher than in reality it turns out to be. So we're below the line here, and that's also overconfidence on the other direction. But basically it's kind of straight. So we have mostly calibrated quantities. Again, for those of you who follow the algorithmic fairness literature, one of the kind of quirky, interesting facts that comes out of it, which I don't think anyone was expecting, was that if you can compare calibration across groups, and you can also consider precision recall across groups. And you can ask, ideally, people wanted to ask for all the good things. They would like, no differential recall differences, no differential precision differences, and no differential calibration differences. And the sad fact of the matter is, it turns out under certain circumstances, you can't have all of those at once. So that's an interesting negative result. How you want to interpret that is a much more serious question that I have no time to get into here, and I'm certainly not qualified to. But nevertheless, these are quantities that may in fact trade off against one another. Okay, that's actually going to be an important thing. I'm going to finish us up here just by noting what happens in the rest of this, and then I think we should all run away and come back for something else. What's happening in the next bit is I'm fitting another model. This is just going to be the naive Bayes model, and it's going to look incredibly similar, so I'm not going to go through it. On the other hand, it is going to give us some kind of more concrete view of a dictionary for which words do what in this case. We're going to evaluate it. It's going to be slightly worse because that's normally true. We're going to look at its calibration, and the key thing that we're going to learn here is that that model is kind of terribly calibrated. That is to say, our naive Bayes model, because it's doing all its work elsewhere, is actually incredibly wrong about the probabilities of things. So this similar calibration curve for the same data set on a naive Bayes model looks like that, which is a mess. Right? You really shouldn't trust any of the probabilities from this thing. Maybe the categorization is okay, but it is not appropriately uncertain about stuff. And that's because basically, if we look at the sorts of probabilities that that kind of classifier puts out, then it's mostly very, very sure that the probability of positive is 0, or very, very sure that it's 1. And that's kind of craziness. That's over certain. It should in some sense have more uncertainty here. However, what we would actually do in practice is say, yeah, that's kind of okay. Maybe it gets something the first classifier doesn't. So we could just combine them, make an uber classifier, a macro classifier, an ensemble method, although with an ensemble it's excessively small. So that's what we do here. We're just going to learn some mapping here, slightly arbitrary. And what you're seeing here is precision and recall for all possible thresholds here. So however important you think precision is, however important relative to recall, puts you at a point here. Use lines as one of these classifiers. And so as you see, they trade off, 1 minus precision against recall. But if we combine these classifiers, you get that red line, which is the one on the outside, pushing in the right direction. It's actually better than both of them. So yay, a model combination. But this takes us into the realm of machine learning. So we're not going to do that. What we're actually going to do is I'm going to sit here and answer some questions, and then we are going to run away and take 15 minutes for whatever counts as lunch. Cool. Questions? Right. Question from the chat. In pre-processing, the words weren't stemmed or lemmatized. Should they be considered? Yes, absolutely. Consider away. Would they be additional features? Definitely not. They would be almost collinear with the other ones, so you wouldn't be adding very much information. If you stem them, basically you would stem or lemmatize a word so that it looked more like words which were intuitively like it. So for example, all the different tenses of the same verb ideally will get collapsed. And so we're only counting the verb, and we're not counting, for example, the tensing, which might be on the end of it. That would be a reason to do stemming. And that's going to shrink our number of things that we count, because we're now going to treat more things the same. So things that would otherwise be lexically different are going to be the same. And that's usually why you would do it. So you want more useful features. And you hope that that's somehow useful, that tense is in fact not diagnostic. Maybe it is, you don't know that, but like you're betting that it isn't. And you are, you're going to drop it in. You could put all these things in. One of the quirks of high dimensional spaces is that they have is that your intuitions about them are probably wrong, because almost everybody's intuitions about them are probably wrong. So there is the larger the number of features we have, in theory, that makes everything harder, and we have to regularize harder because we need them to keep them under control, because we only have the same number of documents to try to learn this relationship. On the other hand, our classification task is easier because separating things in 2 space with 2 words is in fact much harder than separating anything in 6,000 space, because 6,000 space is quite empty and lots of words don't occur. And so it could be, in some sense, a blessing of dimensionality that it's easy to find the decision boundary. Unfortunately, it's easy to find lots of them. And some of them are really terrible. So hence our regularization. That would be sort of to explode out the feature set. What you're suggesting here is like make more features. So in general, maybe don't do that. You actually want better features rather than more of them, or a really good way of keeping a massive feature space under control. For this, the literature you want to look at is like support vector machines and specifically kernel tricks, which are the two related ways of blowing up the feature space such that the task is easier, and then putting the appropriate model structure in so that you find a decent decision boundary. But that's well into machine learning at that point. Question in the chat, is linear probability with text data also possible? Yeah, everything's possible. So the nice thing about, well, one of the things about the way we are thinking about text is that as soon as this turns into DFM or some function thereof, you could not tell that it came from text. We're just treating it like data. The whole deal with like text as data is that we've stopped caring that it's texty. Text has certain distinctive difficulties. That's certainly true. And there are distinctive models that may fit it. But we're trying to kind of like generalize from them. So anything that you could do to like general purpose, many featured small numbers of cases, data, you could do to text. The case in point here, looking forward, I won't mention this in the slides, but I don't mention this in the slides, but topic modeling as a way to think about topicful documents was sort of simultaneously invented by people who wanted to figure out where the topics were in a document, but also people who wanted to do kind of map patterns of genes. So the alphabet's very small at that point. But the same class of model turns out to be quite useful for both of them. And you can have topic models of images as long as you define what it is that you're interested in counting. So sure, absolutely, linear probability, why not? What you shouldn't forget is the regularization, because that will all just fundamentally break if you don't do that. All right, so let's genuinely take that. That was about 5 minutes of my 15. So I am going to turn my camera off, take an old man bathroom break, and come back to you in 10 minutes. Oh, 15 minutes. Thank you, whoever it is that wrote that in the chat.
My name is Carlos Ahumada. I come from Mexico, and since 3 years ago, I live in Berlin. Currently, I work as senior strategist for data and analytics at Cosmonauts and Kings.
My name is Hannah Miles. I'm from the UK, but spent many years living in Germany, and now I'm living in Vienna, Austria. I work as a statistical analyst at Ground Truth Solutions, an international NGO based in Vienna.
I'm Malte, I'm from Berlin, and I'm a data scientist at the Looping Group. My daily work involves analyzing data from social media and other publicly available data to understand what our clients' customers are passionate about.
We use data science to improve the humanitarian system. We want to understand how people affected by humanitarian crises experience the aid they receive. So we conduct surveys to find out what works and what doesn't, and then we challenge and support aid organizations to implement this feedback and make improvements.
Before coming to Berlin, I worked as political advisor in the Mexican Senate and at public affairs consultancies in Mexico. That's where I started realizing the need for quantitative methodology and data use for making public policy, for designing political communication campaigns, and so on. And that's when I started getting curious about data and all the possibilities that it has for this field.
I got into data science at the Hertie School through the initial courses in statistics and economics. I did not come from a mathematical background, so it was something new for me that I really enjoyed learning.
I think that without the Hertie School, I would have never chosen a career in data science. I found my passion for statistics and for quantitative methods.
So I do a lot of hands-on data analysis in my day-to-day work. So the practical elements of the courses at Hertie have really helped prepare me for using Python and R in my day-to-day work.
For me, there's really a before and after the Hertie School. Not only I met fantastic people in this school, but also it gave me the right tools and skills to succeed in the data science field. It gave me the methodology and the knowledge on how to work with data, but also how to apply it into our political field and for solving real problems.
Most of all, as coming from a humanities background, what I really loved about the Hertie School is that everybody is given the opportunity to learn something new and something that they've never done before.
Big data allows us to incorporate many more viewpoints and voices into any decision-making process that would otherwise be impossible to process for any single human.
For me, the insights that you can get from data are invaluable, and they can really shift our world in a positive way.
I found out that there is such a thing as scripts. When I visited the website for the first time, the very first thing I realized was when it showed the biggest challenges of the 21st century. One out of two examples was the rise of inequality, and I thought, like, yes, that's exactly what I'm into. So that's exactly the program I want to be part of, and in the end, I got the chance to be part of it. I have to remember. First, I asked myself what we mean, or what they mean, the cluster of excellence and the people behind that. What do they mean by liberal, and what do they mean by script? And I find it very interesting because my first feeling and association was like, yeah, I agree. And then second came, but upon what? So I think this is very important to first of all define what we mean by contestations of the liberal script. And second, then go for it. But yes, the liberal order and the liberal script, these are definitely things we should think more about, as we have maybe kind of a feeling. But does liberal script mean the same for us here in Europe as it does in the United States or in Latin America? And what are the contestations and so on and so forth? To agree upon that, I think it's a very important part, or it's a very important work which has to be done. I hold a bachelor's degree in political science and history of art and a master's degree in political science. And I studied in Kiel and in Berlin, but I was also given the opportunity to study abroad in Spain and in Costa Rica, and to attend conferences in the United States, and to work as an intern at the United Nations Research Institute for Social Development in Switzerland, and in the German Bundestag and the federal headquarters of the Greens. Well, I would say my expectations go into three aspects. It's perspectives. I wanna get to know new and other perspectives, which I know so far. It's knowledge. I want to gather new knowledge, and I also want to contribute to gathering more knowledge about the problems we are facing. And it's networking, because I very much believe into synergy effects, and I would like to work and exchange with other professionals, experts, people from academia that are interested in the same issues as I am. In my thesis, I aim to shed light on the role of the business elite in the context of persistent inequalities, embedded in the debate on contestations of the liberal order. Mexico was already at the beginning of the 19th century, it was called the country of inequality. It was by Alexander Humboldt, I think, in 1811 when he said so. And what I found out, Latin America in general is the region of interest of mine. So I was looking on data, and I realized that the most unequal country, if it comes to income inequality, at the very top, at the 0.1%, Mexico ranks first and leaves others far behind. So I am researching upon economic inequality. Yet on the other hand, the elite so far research upon this group of people is in its absolute initial stage. So, employing a mixed method analysis, I aim to ask for the patterns and the perceptions of the elite as to gather new knowledge about their role in the distribution debate, or rather non-distribution debate, but inheritance of inequality. What brought me to the topic of inequality, or to start one step before that, actually what brought me to political science was when I was traveling for the first time South America, and I was volunteering in an orphanage in Santiago de Chile, and I simply realized this huge social inequalities there. So I was aiming to focus and to concentrate on the social and political and economical issues that are underlying this phenomenon. So I started to study political science before, and I wanted to study other stuff. And I'm happy with this decision. And what I realized that there is one cross-cutting theme going, like really cross-cutting all the others. Like, I mean, economic inequality is also seen as, or is actually framed as, one of the sustainable development goals from the United Nations. And it's stated from them very much themselves that if we don't make the trends we see and observe right now going into another direction, avert them, we will not be able to even reach out for the other SDGs. So inequality is really the thing we have to face, we have to tackle in order to be able to solve the other problems we have and we have to face.
Our alliance wants to tackle societal challenges by academic excellence in civic engagement through social sciences. Foster a new urban generation of European leaders. European citizenship is also a main part, and basically to include students and public at the center of the idea of Civica. The benefits of multidisciplinarity is definitely tackling solutions from various perspectives. That's why Civica always fosters the idea of complementarity, but also overcoming differences. I like the increased mobility, and I like the new opportunities that Civica brings me with various faculty members, joint courses, research hubs. European University aims to educate people in a very interdisciplinary way, promote research and innovation among students to prepare them for the future and to be competitive in the job market.
Ahoy, and we're back. Right. Let me catch some, oops. Let me share my screen. Right. Let me answer some questions that I saw previously in the chat about the regularization. Yes, we are trying to keep the coefficients at reasonable sizes, mostly because they're going to overgeneralize things which shouldn't be generalized. One quick analogy might be if there are only two words that you see, there's a, let's say we're in a LibCon example that you saw before for the amicus briefs, and you had the words discriminate and societal or something, then you might discover that, that a whole bunch of documents contain only the one and not the other, depending on whether they're con or lib. So we would have a perfect separation between, we would have in some sense perfect predictors in the training set for which words mean which words associated with which label. However, we don't expect that the relationship in the training set is likely to be true in the real world. Things just aren't that sure. So if we're regularizing, we're stopping the coefficient putting so much weight on either one of those by basically forcing it closer to be zero. It might want to be extremely large, but actually we would like it to downweight the amount of information it thinks it's getting for seeing any of those training set diagnostic words, because we believe secretly that it's in fact not as diagnostic as the training set would make out. So indeed, that's just regularization. Okay, find the chat. And right, so let's do something else. In fact, let's do two other things, depending on how much time everybody has available, or until I get cut off by Olga, which wouldn't be honestly entirely reasonable. Okay. Right, back to this. So that was that was document classification, but let's think about the situation where there are we don't have one topic per document. We have actually loads of them. So here's a nice diagram from a schematic, should we say, from Bly, an early paper on topic modeling, which is what we're going to talk about now. The idea here is that when we look at that text, what's actually happening is that some of those words are associated with topics on the left. And what we'd actually like to know from this text is which go with which. And finally, we want to know for each, the message that this document is trying to get across is effectively the bar chart that you see on the right-hand side, which is saying something to the tune of, you know, this document contains mostly whatever the yellow topic is, the gene, DNA, genetic one, quite a lot of the life evolve organism one down below it, apparently none of the green one, and like a little bit of the blue. So that proportion, how much I emphasize one topic over another, is a fact about the document, which I think generated the words that we actually see in it. And what we're going to try and learn or assume is the relationship between the words and the topics over there on the left. It's going to be the dictionary when we know it, and it's going to be the topic model betas when we don't know it. And the facts about the documents, we want that theta in this case is going to be the balance of things that this balance of topics that this document talks about. So the question is, can we learn any or all of this? So to be concrete here in our little diagram, we've just changed the assumption about the model. So you'll notice there's still theta over there, but rather than there being only one topic, in fact, every single word has a topic associated with it. That's why they're both inside a plate. So there are n word topic indicator instances. We, of course, don't see the word indicators. And if we want to know how to generate a word, then it's something to do with what the Z there, something to do with what topic that word is about. And we only know which words we're expecting to see because we have a quote dictionary, which has sort of a recipe over there on the betas, which said, okay, you want to talk about topic K, the defense or something, then here are the words that you are going to generate with probabilities. And if we switch topic, and we get the same words but different probabilities, so we have a complete story. That's going to be the exploratory version of this. So if you need to see this more concretely, then we think about it happening down at the bottom. There's our previous sentence, and we're imagining that there's going to be a topic indicator that we can't see. It's going to be Z associated with each word. And so the question is, can we aggregate that whole thing up into the representation of the meaning, which is in mostly the third. This document is mostly the third topic, and a little bit of the fourth topic, or whatever they are, and not much of the other ones. That would be a sort of a standard way to think about the message in this case. Okay, so actually, I mean, what do we want to do with these topics? Well, ideally, let's just say a few things about what we could do with them, on the assumption that magically this whole thing has been fit and we get assignments of topics. So typically, we're going to take a bag of words approach. So we're not actually going to roll down word by word. We're just going to want to know in aggregate how many of each of these topics we use. So how much of the document's about defense. We might want to do scaling, or like try to figure out substantively on a kind of left-right dimension where this document is. And we might do that not by going directly for the scaling, although we'll do that later, but by saying, actually, here's a bunch of topics which are righty topics and lefty topics, and I'm just going to kind of subtract the proportions, and that's going to be a very crude but possibly interesting measure of position. So how much do you emphasize one over the other? And in general, we're always going to be thinking about relative proportional emphasis here. I'm going to try, but we're either going to know or learn what the topic-word relationship is underneath. This is a hard problem, particularly if you don't get any topic labels. So hence the discriminative version here is going to be very helpful. So you've seen this before. If you've taken a kind of a classical political communication course, then you've probably seen this, which is Gamson and Modigliani looking at a whole bunch of American newspaper text, and in this case manually, but it doesn't matter, saying, okay, you're going to talk about nuclear energy, but how are you going to do it? And these are in some sense frames. Obviously, the analysis that Gamson and Modigliani are doing in terms of frames is much more complicated than anything we're going to do, but the key point is what you get out of the end is proportion of these sorts of ways of talking about nuclear energy, which may as well be topics. More nearer to the present, we might also have this is a more discriminative, again, a discriminative exercise where someone has gone in, Voigt and colleagues, built a little dictionary which says these are the sorts of words that you use in a police stop when you're trying to be formal, or when you're trying to be polite, or whether you're trying to be impolite. And so we're going to apply these to transcripts of stops. And then the interesting analysis is not actually in the application of those. We're just going to assume the dictionary works. But in taking documents, in this case, stops with people of a particular race being stopped, and then compare them. And so if we see differences, then if our measurement strategy is right, if the word mapping for formality does in fact work that way, then we have a measurement device for comparing groups. That's actually a nice paper worth reading. So we're going to have two directions, as I mentioned before. There's going to be a generative version where we don't assume that we know anything. We see the document feature matrix. There it is, W in the middle. It's N by V. So what we're going to do is try to learn both the indicator variables, the Z, the topics, and also what those topics map to words as. So both beta and Z are going to be learned. And what we get out of the end, obviously, is the proportions. On the other hand, we can think in the discriminative mode, where we know what we have some ideas about what the word topic mapping is. And so we can actually kind of parameterize that directly. And so what you see on the right is the discriminative version, where you're saying, okay, I see this word, and if I want to know like what topic it is, then I'm going to look up in my dictionary, that's beta up there, which I claim to know. Okay, I'm just going to assume that I know that mapping and write it down. Not even learn it, just actually assert it. And those two things together, knowing the identity of the word type and knowing the dictionary, is going to tell me exactly what Z should be. Then it's kind of trivial to figure out what the proportions are, because we know everything, right? So we have a dictionary that we know. A question in the chat quickly, what about negation? Yeah, what about negation? So one of the features of this Texas data as a strategy is that it relies on the fact that people don't tend to disagree with one another simply by negating the other guy. So I don't in fact object to your point by saying not that. And now that's, I actually make a separate point, or I talk about something else. And so that is distinctly genre specific, I want to say. So it may be that in certain like technical contexts, or for example, fine tuning legal ones, then actually having a not in the middle can just change everything, and that's fine. In the slightly looser, more political scenarios that we're dealing with, typically people won't negate other people's words, they will simply use other ones. You can think about this as from an information perspective, in that if an innocent bystander wanders by this discussion, how are they going to figure out whose side is who? They have to track not, and that's quite hard to like catch in things. So if you want to be maximally unambiguous about what it is that you're trying to get across, then you don't actually use all their words and then put not in the way. That would be counterproductive. But that's just a strategic story which I cannot validate for you, but merely by way of intuition. Okay. Can you put them in the Tata models? Yes, you can. You can always add negation. It's a new word. Here's the word, and here's the word with not in front of it, and they're different. That's actually what the sentiment dictionaries often do, or you can like look for that phrase. Okay. So what if you knew? So let's assume that you know. So we're gonna do the right-hand side one here. We're gonna assume that you know what this dictionary is, and then we're gonna do things with it. And then we're going to work on the assumption that we don't, and that's what we're going to go into the exercises with. So it may feel a little bit odd to think about these as the same model because one is considerably older than the other one. So what you see on the right is dictionary-based content analysis. And that's been going since there were computers, basically, since the early 60s with the General Inquirer, which is Phil Stone's device that ran at Harvard on punch cards. That's a very early form of this dictionary analysis. And the topic models turned up much more recently, but they are fundamentally making the same mixture of topics assumption. So let's start with the easy one first. So if you look at a content analysis dictionary, so-called, then you'll see something like this. Here's this is Laver and Gary in 2000 writing about British politics. See a minor obsession here, maybe? Yeah, no. There's lots of categories in this dictionary, but the two that we care about, just because the slide is small, are whether you're interested in state regulation of the economy or whether you're interested in sort of market solutions to things, which ought to be a sort of left and right side of things, but they're economically substantive. So the idea here is if you see accommodation, age, ambulance, assist, whatever, you're into state regulation of the economy, lefty things. And if you see assets bid or anything beginning with choice, choice-based, competitive, all that kind of stuff, that's on the kind of righty side of things. And if something occurs that isn't in any of those lists, it didn't happen. It's just not interesting. We've just asserted that it doesn't matter. So how does this turn into the kind of generation assumption? What do we have to assume about how words are generated for this to be true? The reason I'm going to do this is because there's a particular awkward flaw in these dictionary methods, which leads to all kinds of difficulties, which is specifically to do with this problem. So here's a thing. What you're actually saying when you write this dictionary in a content analysis context is you're saying, here is the posterior distribution of topics per word, given that I see a particular one. So what's the probability that I'm reading something that's expressing state regulation topic, given that I see the word age? And the answer is 1. It's definitely state regulation, and that's just the end of it. And it has probability 0 of seeing market. So it's very sure. In the naive Bayes example I gave you before, that was a classifier that was absolutely dead certain about things, and that kind of was a little bit hazardous. And this also be a little bit hazardous here. But nevertheless, if we're sure of it, we'll just assert it. Conversely, assets, yep, see assets, definitely on the other side, and 0 probability there. So if that's the posterior distribution, how would you have to talk? And the interesting thing about this class of model is that it's entirely indifferent to how often, if you're trying to express state regulation, you do say the word age and benefit, or how often, if you're saying market economy, do you say assets and bids? And I've replaced numbers here with letters here because it literally doesn't matter what these numbers are. They just have to be not 0. So any story about generation where you do talk about age and benefits and you don't talk about assets and bids is good enough. So in a certain sense, they're a bit agnostic. modeling from a modeling perspective. That's kind of cool. What's not kind of cool is that the only way you can get those posterior probabilities to come out right, the only way the generative story could work is if you never, ever, ever say age when you're talking about market economy. So it's actually the zeros that do the work here. So these zeros over here. So these can be anything you like, but these have to be zero. Otherwise, we have measurement error. And one of the consequences of measurement error is that if we tend to get the wrong categories mixed up together. And so when what looks like let's say what looks like 90 to 10, one category to the other, if we have a little bit of leakage, as it were, into the other category count, then we're going to kind of get closer to 50-50. So we have the usual attenuation from measurement bias if we're wrong about these zeros. And in general, we're wrong about these zeros. But that's a kind of feature of having to assert it yourself rather than learn it from data. So what we should do is have a look and see whether we could, in fact, get around this by learning the whole thing from data, try to learn the dictionary forward and then use Bayes' theorem to back out what Z must have been for any of those words. Okay, so we actually need a bit more machinery here. I'm not going to say very much about the machinery because it's well covered in lots and lots of places. But suffice to say that the general problem of learning a dictionary with K categories in it, and also learning which words are associated with or what the proportions of each of those categories is in a document all at the same time without actually kind of any help is, at least in the abstract, basically impossible. So we're going to need like a bit more model structure assumptions essentially to make this go. Traditionally, so this is the latent Dirichlet allocation model that I'm showing you here, possibly the simplest kind of topic model we could think of that's actually stochastic. And even there, we're going to make multinomial assumptions, for example, about the dictionary. That's going to be a die which rolls somewhat weighted depending on which word, tells you which word to generate on the basis of which topic you're trying to do. But where do those probabilities come from? Well, not out of nowhere. So we have these so-called hyperparameters on the side which say, let me regularize, again the word, let me smooth these out so that you don't try to like overlearn what the word relationships are. The smoothing is going to be done by Dirichlet distribution. This not being one of those courses, I'm simply going to point to it and say that is what stops this model trying to both overlearn which the topic word relationships, but also admits to the fact that actually a lot of these topics will also use words that are in some sense belong to the other topic. So it sort of allows a bit of mush there, which is very helpful. Also, the math works out a lot nicer, but that won't detain us here. Okay. For our purposes, from purely practical, introductory sort of purposes, the thing to know about these things is that that's a model that can take a little while to fit because there's a lot of coupled unknowns. And if you want some intuition for like why, how you would fit one of these models, because it seems like you're getting nothing out of something, which seems strange. The idea is basically there's a whole bunch of parameters. And if you were to know if you were suddenly to kind of peek behind the curtain and you were to see what the topic labels for all your words were, then it'd be pretty easy to figure out what the dictionary must be and therefore what the proportions of the document for each of those topics was. Conversely, if you actually knew those parameters which generated those things, then inferring what the topic proportion for any particular word would be pretty easy. So the intuition basically is you could start with the one sort of randomly and then do the other one and then alternate. So that's going to take you into a Gibbs sampling framework in a simple sense. We can do it more efficiently, but the intuition is just that, we're going to alternate between saying we know the parameters and saying we know the topic assignments. And that's fancier versions of that are what's going to be happening in the exercises. Right. A question in the chat about actually the dictionaries is a very good question. I'd like to ask how researchers compile a dictionary. Words can never be exhaustive. Yes, that's true. So if you're worried about exhaustiveness in a dictionary, then you're worried about recall. You're worried that I'm busy making this point, but I'm using words that your dictionary doesn't know about, and so you're going to miss it. That's the concern there. So that's the exhaustiveness. On the other hand, if you fill a dictionary full of words that I might even slightly use to talk about my particular topic, then what that means is much of the time those words aren't actually about my topic; they're about something else. Which means that if they're assigned to my topic, then they're in some sense measurement error. And what we have there is a precision error. So the dictionary says, if you see that word, he's talking about that thing, and the answer is. Most of the time, he's not actually. So that's a precision fail. So that's what I mean by recall and precision trading off. I can make a huge dictionary, I get very high recall and very low precision. Or I can make a very fine-tuned artisanal dictionary, which has hardly any words in it, but they're absolutely guaranteed to mean exactly the topic that I want. Although I'll miss most of the language that's about that topic because I don't have delightfully chosen words for it. So that's the trade-off. It's a precision recall trade-off. Unfortunately, you have to do it by hand in the manual case, which makes it hard. In the precision recall trade-off that you saw in the previous exercise is a little bit easier because at least you kind of like, you know which direction you're going, and you can threshold things, and like you have levers and knobs and dials where you can affect what the precision recall properties are. In this case, you're just adding words and seeing what happens and then checking, which can be kind of exhaustive in the other sense. Yeah. One kind of cute thing to do is to run the topic model first and then try to extract from it what a dictionary would look like. So you can kind of use the exploratory thing to help you with the confirmatory thing. The key in all of those sorts of situations is not to fool yourself. That is to say, not to do this all on the same data set and then hope that it works later because you will overfit what you're working with. But done carefully, that can be a very good crutch to generating a confirmatory, targeted, what I previously referred to as artisanal dictionary. The research problem determines which one you want. Do you want high recall or do you want high precision? If you need to catch stuff, you want high recall. If you want to be right when it says you, when you think you are, then you want high precision, hence smaller dictionary. Our topic models don't care. They'll give a probability to any word for any category. So that's not really the question here. Okay, so what do you get? So let's just be like super concrete about this. What we get out of this is we get betas, which are they're actually going to be the probability that this topic generates that word. So it's going to be a beta per topic, be a vector of betas per topic. But those are much too hard to read. So one thing we'll end up doing in these sorts of exercises is summarizing somehow what this model thinks are the kinds of things that you say if you're in topic K. And one of the ways to do that, not necessarily the best, there are several, is to pick the words that are most probably generated from that topic. So the ones that are highest probability if you were talking about that topic according to this model. And if we just list them, these are stems that you're seeing from Quinn and colleagues' model, then that's what you see there. And the idea here is that on the right-hand side, that's actually what this model has decided is a topic. You unfortunately have no control over what it is, but you do have the task of interpreting it. And so knowing what it tends to generate would help with that. So from staring at the keys on the right, Quinn and colleagues generate their own short label. And the important thing to know here is that they generated that label. So you have to believe it. They have to believe it. And that's an occupational hazard of learning the whole relationship is that you don't really get that much control. I'll say just a little bit at the end about ways to kind of get the best of both worlds, but in this case, we're fully exploratory. All right. The other part of the output is the proportions, but the proportions of each topic in each of those documents. So let's concentrate here again, same paper, on one of those topics, which Quinn and colleagues have decided is the use of force. It's words apparently associated with the use of force, and we're going to look at it just that one proportion for all of the documents that we've got here, which I think are Senate speeches, if I remember correctly. So what we're plotting here is actually it's the number of words. So it's going to be the length of the document multiplied by that proportion. That's going to be the number of words on that topic, inflated up from the proportion, as it were. So that's the Y, and then we've just like plotted it against time. And the idea here is if this really was the use of force, then we ought to see things in the real world corresponding to uses of force turning up in the models of you about whatever that topic is, let's say it's topic K, and then they've labeled these things to say, look, this is really actually like what's happening. These big spikes do correspond to things in the real world, a certain amount of measurement validity for it. Ideally, you'd probably want a placebo test on these things in the sense that there may be uses of force that are in here, and you would want to know where they were before wondering where the proportions are. But this at least this is something. Okay. So the key thing here is like, we've left control in the exploratory sense of substance. We no longer have control over the substance of the topics. So if you're looking for a little bit more control, whilst taking into account the point in the chat that exhaustiveness in dictionary assignment is just kind of tough, then you can think about key ATM, or you can think about seeded topic models, or various ways to kind of drop your own favorite words into one or other of the bins of topics and say, maybe that. How about you kind of like work around these, which I'm fairly sure ought to be in this topic. That's harder than it looks, in the sense that models that are somewhere between exploratory and confirmatory are also a bit tricky. You also don't entirely know how replicable these things are. So let's say you drop a word in and then you get some result, and then you take it out and you get a very similar result, then which one do you report? Who knows? But there it is. So maybe actually the right way to think about this is all on the way to confirmatory. Okay. So as you might be getting the impression, there's an awful lot of interpretation going on here. So how would we do that? We can think about this in two ways. We can think about it statistically. So we can, it's a model, it has fit characteristics, it has out of sample prediction, all that good stuff that a statistical model would give you. And then there's also human or substantive evaluation. Put bluntly, it doesn't make any sense. We can also think about two natural levels here, right? So are we asking how good this model is, period? Or are we asking how good is that topic? Is this really like, is this good at the sort of topic word level? One of the big takeaways for this literature is that these are not well aligned. So you would hope that you could improve the statistical fit and also get more interpretable stuff, and you'd be wrong. Now, for my money, actually, substance is what I'm interested in. So I don't particularly mind that this is statistically, I would be choosing a model that's statistically a bit weaker, but your mileage may vary. Okay, so this is Quinn trying to figure out what on earth the whole model is doing. So we're taking in this case, he's taken all the betas for each of the topics and just cluster analyze them on the assumption that topics which he thinks are kind of all defense should hang together and all judicial should hang together. If they do, he's kind of happy. It's kind of very informal, but nevertheless a useful way to get at these things. We can also look at the statistical measures, and indeed it's kind of easy to generate. Out of sample testing is one way to do it. The package we're going to work on in the exercises called STM, the Structural Topic Model, calls it held out likelihood, and has a lot of functionality for doing this. So it's kind of nice. So a standard bit of output might, in the STM case, look like this. So one thing we should ask ourselves is, okay, we only have control over essentially one thing. How many topics do you want? That's it. That's the after you've generated your DFM, that's the only topic model kind of parameter, at least in these simple models. So one of the tricky things about this is that a natural question for you is how many topics do I need? And a natural question, and the model can answer this in some sense using held out likelihood. We can say, okay, if I add another topic, do I fit the data better? And the answer is basically always yes, all the way down to like thousands and thousands of topics, or until you run out of serious data. So you'll see the held out likelihood going up and the residuals going down, as you would expect, and all kinds of other good stuff. And you just keep on adding more topics. Sadly, there's no guarantee that any of these topics kind of mean anything that you want, even though the model is fitting better. That bottom left is the kind of giveaway there for a kind of a coherence measure, about which we'll talk about later, slightly more substantive question. It just kind of goes down. So from a semantic coherence perspective, maybe 10 topics was pretty good, and 30 was pretty bad. But from a probabilistic perspective, 30 was great, and 10 was worse. So what you get is, yeah, sentences like this. This is a great piece from Justin Grimmer, saying, yeah, well, we kind of did some things, and then I chose 43 issues, and that seemed like a decent middle ground. And you might say, what is that about? But no, that's actually more or less what you want to do, because if substantive stuff matters, then a decent middle ground is your expert opinion in some sense, and you can hope to get to use the like an objective measure, but those objective measures are not actually probably measuring what it is that you hope they are. Okay, so at least from my perspective, we can be realists about these models, or we can be anti-realists. That is to say, we can say that model structure that I told you was reasonable, and it's true, and like somewhere in the world there are topics, or we can say, okay, I'm going to take a document term matrix, and I would like you to tell me what it would look like if it were in fact a mix of 40 topics. But I can also the next day, or in fact, in our case, in the next session, say, what if it wasn't a mix of 30 topics? What if it was everybody lining themselves up in some space or on some line? And then I can get a different answer. And in some sense, I'm just choosing how to look at this thing. I'm not particularly committed to there really being topics or really being positions in there. I'm just applying this model and saying, let's assume, okay, is this illuminating? So it's the utility of the model for downstream purposes that's interesting. But that's me. Okay. So there's somewhat detailed ways of figuring out at the topic level whether things are any good. For one thing to do is to get humans involved and say, actually, here's 5 words from allegedly topic K, and then another one which I've snuck in, which is in fact from some different topic. Can you tell which one? If you can, probably is a coherent topic. And same thing with topic precision. I could offer you a chunk of text, and I could say this model thinks it's this is a mix of topic A, B, and C, and then I could put topic Z in there as well, and you could say, well, I'm not sure there's any Z in there, and then you go, excellent, these topics are really good. These people can even spot when there are interlopers. So we can formalize those a couple of ways. This is with humans. This is actually like experimental evaluation in the lab, as it were. But we can also have certain sort of statistical shadows of those operationalizations of those which don't require people. The ones that are going to exercise us in the exercises are going to be frequency, exclusivity, and Frex. Frex is the combination of these. So we might ask ourselves, if this topic's any good, then it's got a bunch of words which really only occur in this topic and don't really occur anywhere else. Nice separation. On the other hand, if they're really low frequency, that's not very hard. So they should be decently frequent and yet somehow diagnostic of this topic. And to the extent that I've got that sort of topic where it's like nice blocks of vocabulary, more or less sort of distinguishing the topics, then I've got high Frex, as it were, like decent quality topics. We can do similar things for semantic coherence. So the Frex model is just a way of like figuring out what that topic is, but also evaluating it. Okay, a question from the chat. Am I right in thinking about the right case like trial and error with human interpretation in a substantive way? That is your choice. I personally would do it more that way. So if the purpose of having a topic model is to get at a particular topic, and sadly that is actually in social science applications usually what you want, secretly you know what you want, and you're just fitting this topic model because someone taught it to you in a text analysis seminar. And also you don't necessarily know what vocabulary is perfectly associated with it, and so you're going to run this guy first. If that's the case, then you have a slightly different, should we say, objective function to the topic model itself. It just wants to fit the whole data, but most of that data is about stuff you don't care about. because secretly you just want to know about that one, or those two. So in that case, yeah, you're kind of on your own there, because if you follow the statistical gradient, then you'll get a better model in aggregate, but it might not be better for what you want. And if you but you can use these kind of topic quality indicators to guide your search. So maybe you're actually staring at one or two topics and trying to get them nice, in which case, yeah, choice of K may be different. But indeed, yeah, a certain amount of trial and error here. I mean, it's an exploratory method, right? Fundamentally. And trying to make it a non-exploratory method is a whole industry, which can be very disappointing, at least in my experience. It's just hard. We'll see an example of how we can make it less exploratory in a moment, but only relatively so. All right, so the big takeaway here is, if we think about the x-axis here on a whole bunch of corpora and problems and whatever is being left to right gets statistically better, and on the y-axis, substantively nice, higher is better, then almost all of these measures are negatively correlated. This is from Chang's paper, which reading the tea leaves, I think it's called, or something very similar to that. It's in the references. Somewhat an older paper at this point, but a classic. Can we understand topics, asks someone in the chat, we're not substantively interested in, but that are important to the model as control variables? That opens up a really interesting set of questions about causal inference text, which regrettably we will not have that much time to talk about. I would suggest there's a nice paper by Agami and colleagues on causal inference with text. I'm sure there are others, but that's a decent one to read about how to think about using specifically topic model, or very nearly topic model measures, either as treatments or as controls or as outcomes. Yeah, it's tricky. So what makes it partly tricky here is if you're interested in that topic and there's these other guys over here, then notice everything has to sum to 1 because the proportions just do. So we can think about it's hard to think about the control. It's hard to think about things varying independently when they are in fact proportions that must sum to 1. Put another way, when you emphasize one topic, you de-emphasize everybody else, or maybe you de-emphasize one in particular, but there's a negative correlation, which you saw in the very first slides there, which makes it quite delicate to think about. To think about the normal kind of interpretation of regression coefficients, where you would love to say things like, maybe I move that and hold everything else constant. That's often not, doesn't make that much sense. Right. One thing I want to say about this is, if you think you're doing the same thing in your content analysis and in your topic model, then sometimes you can just compare. So here's a slightly awkward but fun paper by Wouter van Attenveld and Crowd at the I think presumably still at the Free University in Amsterdam. The idea here is we take that nuclear power thing that I opened us with and said, okay, are these the way to talk about nuclear power? Well, let's do a topic model of nuclear power stories and see whether we get the same topics in some sense as Gamson and Modigliani did. So what you get as topics labeled by Attenveld and colleagues is on the right. And the runaway themes and all that kind of stuff is on the left. And if you do code it, then you find that the topic model is the appropriate topic model, or something close to it, actually generates a whole lot more detail than Gamson and Modigliani do. The other thing that you'll notice about it, and this is a salient feature of topic models, is that implicitly when you think about topic models, you think about themes. But the topic model doesn't. It only thinks about things that are conditionally independent if you were to know they were in the same category as mixed up in the sorts of documents they tend to turn up in, which is a much longer description, which isn't the same thing. So one of the notable things about the stuff on the right is the prevalence of events. So Gulf Wars, Cold War, particular films, NATO as an organization. And that's because NATO as an organization would turn up as a topic. If you give enough topics, then there'll be something about NATO language. That's despite the fact that it's not a theme in any sense. It's just a bunch of words that bundle together, and this topic model thinks as a topic. So that's partly why you don't get the same topics here, but also they don't map onto one another very nicely. And again, that's kind of general. Okay. Last thing I want to do with this this theme is say, okay, maybe what you'd like to do is have a little bit more control over what these topics are. And in particular, maybe you have things in mind, you're pretty sure they're in there somewhere and they'll pop up as one of the topics, but you have facts about the document, docvars, as we called them previously, which would explain why you see more of that. Or put another way, you have this topic, you kind of like it, and you'd like to know how it relates to, I don't know, partisan identity or gender or something like that. In which case, you have like a regression problem, which is related to partisan identity or gender. And then you have the measurement problem, which is find me topics. We can bundle these things together. And that's what we get in a structural topic model. A useful thing, not because that's the only way you could do these things, but because it's a picture of a pretty standard social science kind of question. So I know there are topics, I'd like to infer them. I don't necessarily want to build a dictionary, and I want to relate them to something else that's like real worldish. So this is actually an example from Catalinak on a change that happens in the house in the way you would campaign for your house position in Japan, which happens historically at a particular point. And ought to, at least in theory, change the content of the platforms that individual legislators put out. So you're looking for a change in the proportion of discussion of things you can generate for your district versus like things you're doing for your party. And here, this is kind of pre-structural topic model. So that change you see on the right, previously you fit the model, get those two proportions. There's going to be two columns of theta, essentially. One of them you can identify as what she identified as pork, and the other as policy stuff. And then we're going to kind of just do a regular old regression model separately. But in fact, what we'd quite like to do is this whole thing together. So we get this kind of model, which is perhaps the most complicated of the DAGs we're going to see today. It's basically a topic model, so that's still the proportions of each of the topics. But now we'd like to predict what those proportions would be on the basis of something I know about each document, some docvar, some covariate, and then there's a regression coefficient, and it's called that because I ran out of Greek. So normally you call it beta if it was a regression thing, but hey, beta's over here, doing exactly the same work as before. So the crux of this thing is we're going to get a topic model and also a regression model that connects to the topic proportions, and that'll be a little bit easier to see in practice. Right. You should be aware that there's a vast literature on topic models, and yeah, more than enough fun to play with. It's the one thing that if I were to give you as a social scientist a piece of advice, find one that has stable code first. That is harder than you would expect. And one of the more interesting recent results from various machine learning conferences, and I suspect that it holds also this class of models, is you only need to make a contribution and do better on one data set to get a paper out of a new topic model. But whether it's actually going to be useful for your purposes, or indeed run on anything else, or indeed stand up to a serious hyperparameter search across related models, is a very different question. So one thing is you should check it has actually stable code and you can run it, and have a certain amount of skepticism that something fresh off the block, which sounds amazing, is actually going to do what you want, at least reliably. Maybe it will, but like delicacy here. And that's just a feature of the incentive structure for a field that advances as fast as CS does. Okay, let's go do these things. So I'm going to practice what I preach in this case, because we are hopefully, if I've remembered to put the data in here, then we are going to be using the same data set twice, this and in the next session, to give us two ways to look at the same thing. So let's have a look at this. Right. So open up our topic thing. Again, this is long, but we'll just do the highlights here. Okay, background. We are looking at again an abortion law debate. This is from 2003. It's in the US this time. You might expect the themes to be similar. They are not, which is kind of interesting in itself. But for our purposes, we're going to see here's a bunch of people arguing about a particular bit of legislation. What do they talk about? So just exploratory terms, and then we'll ask what the different people, speakers from different parties talk about using the STM. Right, that should do us. So I'm going to use the STM package. If you don't have that, maybe install the packages STM, or that will move things along. And we are going to use this US debate thing. Right, so what does this corpus look like? Shouldn't we? So here are our folks. I've again scraped it off the web and bundled the speakers together on the assumption that there's nothing to distinguish their interventions in terms of topic or position. So we have speakers and we have their parties, Republican and Democrat in this case. And there's not so many of them. So this is actually going to be a problem. So previously it was nice to have few speakers because we could very easily see what's going on and we had a model that didn't care, or no models at all because we were just looking at keyness. In this case, it's actually going to be a problem because we've got a big fat model with like 6,000 odd words in it and very few documents. So we're going to have a hard time distinguishing like the balance of topics within these things because there's so little variation across. There's going to be rather little chance of variation in those proportions across speakers. So actually the very first thing we're going to do is change our mind about what documents are. And we're going to do this mostly for statistical reasons. It's going to be reasonable. I'm going to claim it's going to be reasonable to treat each paragraph of these people's speeches as like a whole little document itself. And we know in advance from earlier that that's not going to lose anything because we're still going to know who they are and what their party is and all that kind of stuff. But there's going to be like a bit more cross variation in topics, or at least there's a chance for it. If we did sentence, we could also do sentences, but then our topic model assumptions wouldn't be very good because each of those sentences barely has a chance to have multiple topics in it. So then we kind of don't need a topic model in the first place. So let's have paragraphs as a sort of interesting interim. So what we're going to do is turn that into paragraphs. And as you saw before, yeah, not much changes there. Here's Allard's first, second, third, fourth, fifth, sixth paragraph. Now, one thing, a practical thing that we should care about is if we do that, the paragraph separation algorithm is not amazing, honestly. I mean, it's heuristic, basically 2 line breaks and you're a paragraph. So we should check how long these things are. And if we do that, here I'm taking like all the lengths, so the lengths of each of the paragraphs, and asking how many tokens are in them, and then tabulating that. And what we see here is like how many people have length 0 in tokens paragraphs, and the answer is 15 of these paragraphs don't have any tokens in them, and that's going to be a problem. That's going to break all our models because you can't find topics in nothing. Okay. So we will do our subsetting business for that. So here we're saying take that paragraph corpus that we've just made. And if you don't have at least 2 topics, I mean, 2 tokens, I mean, come on, how many tokens can you get away with? Then throw it away. So that's going to be a smaller version, but it's just not going to break the model. And then finally, let's just kind of do it. 2 things are happening here. We're going to make our tokens, throw away the punctuation, throw away the numbers. drop the stop words because we live dangerously. We could do better than that. We could leave he, she, and it in there, but let's not. And then we'll make a DFM, and we're going to care like very little about this. We're not even going to thin it down. It's just let's go for the least processed version of this paragraph corpus. We're going to wang it into STM. Wang is a technical term in British English, meaning put forcibly. We're going to fit a structural topic model, but actually there's no. We're going to put the predictor variables in there later, but right now we'll just fit an absolutely or fairly standard LD8 model that you've seen in the slides. And for no particular reason, apart from the fact that this is a demo and it kind of works, we're going to have 10 topics. You should feel free to change this around. It's going to be helpful to set this seed, and I should warn you in advance that due to various deep and mysterious awkwardness in other people's linear algebra libraries, you may or may not get exactly the same numbers as I do. But if you do it again, you will get the same numbers as you do. Okay, so we're going to put this DFM in there, say, find me 10 topics, and then we're going to try to figure out what they are, and then see if we can do anything with them. If I'm not entirely mistaken, it won't take very long. Yeah, so pretty prompt. Okay, question is what have we got? So one of the things that we were traditionally interested in is the proportion of times each of these topics turned up. We'll worry about what the topics are in a moment, but just so we can kind of map things on the slide, look at the theta, which is going to be 1,800 paragraphs. Then there's going to be 10 topics. Our output from the document side, the message, as it were, to figure out what it says. So if we have a look at it, it looks like this over here, right? So all those rows will should sum to 1. Yep. So that first one is mostly, allegedly, topic 4, whatever topic 4 is. This is actually a point estimate of the posterior probability, and if you actually wanted uncertainty around this thing, then there's a nice theta posterior function that we could call. We're not going to do that. So we can also look at the betas and see how our dictionaries run, but actually that's going to be very hard to interpret, basically. So what's happening in this little bit of code here is that I'm reaching into this model, pulling out what is genuinely called betas in this model, so mod $beta. But it's very deeply hidden. So what we're actually going to get is log probabilities because the actual probabilities are way too small. And so we're going to get something that's about 10 topics by all of the vocabulary size, which is 3,900 odd. And that's going to be essentially our dictionary. So I do a little bit of sorting and rearranging and find the kind of most frequent ones in this code here, but this is frankly too much work. What you should actually do is use the label topics function. Question in the 2 questions in the chat, which actually, yeah, those are good questions. Can you aggregate paragraphs back? Yes, you can. What you can't do is aggregate thetas back. So you have to do a little bit of work. Now you've got the output in paragraph terms, but it's pretty easy. I mean, you can group by speaker and then average, in fact, since they're proportions. That's a little bit more involved. It's more programming than anything else. But yeah, certainly for the corpus, yeah, you can always get it back into whatever form it was originally because it remembers, which is sort of nice. Is there a rule of thumb that determines the level of document? No, there's a substantive reason that you may. So we should really separate. Actually, let me put this more clearly. We should separate the choice of substantive unit. So the substantive unit is still people here. We are fitting the model on a lower level than people in some sense, but we're always eventually going to kind of aggregate it back up to them because they're our primary interest. So at that point, what we choose as a document and what we choose as the unit of analysis is in some sense decoupled. One rule of thumb here, I wouldn't say it's a rule of thumb, but what we were trying to do was to get enough variation of possible topic content across documents. So you can imagine if there's only one document, and you say, find me 10 topics, then good luck with that. Like, it's a bag of words, so there's no possible way to distinguish it. And if you have two topics, two documents, and say, find me 10 topics, that seems equally hard, right? On the other hand, if you have like a sentence, then maybe that's enough, but there's only one topic in it. So what you're trying to do is make the model assumptions broadly true. Within that, like, all bets are off. Because we can always aggregate up or shrink down. Well, not shrink down. We can always aggregate up to a level of analysis later. So let's use this label topic model. What are these things anyway? What have we learned? Well, as I mentioned before, one way to figure out what we've learned is is to look at these high probability words. So yeah, maybe those are the most likely things to say if you're in topic one. But the most sort of distinctive ones are these: women's rights, doctors, and so, or evacuations and dilations and all kinds of horrors. We should have some constitutional stuff down here as well. Yeah. So that would be like one way to label them if you had difficulty. So one of the bit of code in here, which we'll find kind of convenient, is that we're going to take the output here. This is actually going to be a document, a data frame, so we can pull them out. So this convenient bit of code here will bundle them together and make a label for you. That's just in case you want this code. So there's me taking it and saying, actually, can you take that Frex listing and like bundle them all together and just give me like a string, because maybe I want to make them column names for let's say a theta that I pull out later. Okay. So we can plot them. They look like that, but that's exactly what you were seeing before. And interestingly, if you were doing this for real, then you would try to find. You might be saying, actually, I'm really interested in topic 4. Give me all the documents that are topic 4. And so here's it reaching in and just handing you back the things that have the most 4 in, whatever 4 is, in case you were worried you didn't know what 4 was. So there's a bunch of model checking things here, but let's pass on the model checking things and cut to a slightly. I guess this is going to be our last model here. Let's ask, like, how is there differential usage of these topics? Let's assume that we kind of like them across party. So here we're going to use the actual capacities of the STM, and we're still going to ask for 10 topics so that we hopefully get more or less the same ones. But here, the prevalence, that is to say the proportion, the theta, what we were calling it before, is now going to be a function of party. So we're going to get a large number of little regression models that tell us how party is related to whatever we want. That's just telling this model where to find that party variable. So take it from the doc pairs. So it's going to take a little while, maybe 30 seconds, 45 seconds, and probably about 200 iterations. So I'm just going to let it roll. One thing you will notice is that we get a kind of rolling update every now and again of like the words in this topic. And that can be kind of handy, and you can sort of see them moving around and coalescing in various ways. I think that should be the last thing that we do here. In the meantime, questions about what we've done so far. Right. I guess not. Let's see. So one of the things we wanted was this effect estimate. So how are these things related to party? So the function that we're interested in here is estimate effect, and it's a slightly quirky formula interface. This should sort of remind you of LM, maybe a regular linear model, except the dependent variable is the list of the indexes of the topics that we are interested in connecting to party. So in this case, I'm going to claim that 4 and 8 are interesting topics, but we could have a whole list of them or just one. So we sort of have to decide. Could we do that manually? Ask someone in the chat. Yes, we could. So what you wouldn't get is good uncertainty estimates around, or unless you worked much harder, you wouldn't get correct uncertainty estimates around the regression coefficients, because they're taking into account the fact that this is in fact a topic model estimated proportions, not actually observed. And indeed, it doesn't have the distribution you're expecting. Also in the chat, say, sometimes the topic model can't converge, claiming the matrix is too sparse. Interesting. Having fewer words is going to generally make, or stemming or lemmatizing is going to make that hopefully a little bit easier, but also the matrix may also be too sparse in the sense that you've got documents that are kind of too small or nearly empty. That's going to generate huge quantities of zeros that are tricky. The rest of it is, yeah, difficult numerical debugging. Let's have a look at these guys. So that's going to take a moment, because what we're actually doing is sampling the posterior for the thetas and then running the regression model repeatedly. So how would we do that? So the 2 ways we can look at this are this as 2 regression models. So there's topic 4, which is, and the dummy variable is the party. So if you're a Republican, then you use topic 4, which is mostly Roe versus Wade, constitutional sorts of things, a bit less likely. So the proportion of a document from a Republican is going to have less of this stuff in, is what that's saying on average. On the other hand, there's a discussion of the exact details and medical, whatever the details of the procedure, then you're much more likely to generate that sort of language if you're a Republican. So that's positive and relatively large. Right? So if you flip the party label, you get about 15% more of that stuff, or at least your expected proportion goes up by 0.15, which on a scale of 0 to 1 is actually quite a lot. Okay, so the other way of seeing that is in this little plot, and that's, I think, where we'll probably leave it. So if we zoom this out, what are we actually getting? See if we can make this large enough. Right. So here, a lot of stuff is being done for us. We can compare right, these two. So if you are a Republican, then that is your expected proportion of a paragraph that you spend on this sort of thing on average, on this sort of topic on average, versus that much. More than twice as much if you are a Democrat. So same topic, different party. Conversely, if you very seldom talk about seeing babies in the womb and all that kind of stuff, very little if you're a Democrat, but very much. So almost 20% of your stuff is going to be on that topic, your words on that topic. And those are just the differences, not in a regression framework, so not in a dummy variable, in actual levels. Right. So that gets us, I think, where the STM wants to get us. So there's plenty more here, but yeah, let's leave it there. Actually, there is plenty more. Did I even remove it? Well done, me. Okay. Let's take a couple of questions and then we will go scaling, if you will indulge me for another bit of time. Olga says in the chat, more iterations for convergence. More iterations. Yes, let's do it. Okay, if there are no more questions in the chat, then my work here is done. Then we will launch into other things. Let's talk about putting documents in space. You might ask reasonably, given that I've given you this picture, why on earth you would want a space where everything was connected to everything else by some distance and there was sort of no topical structure or anything like that. But actually that's going to be somewhat useful for many, at least political science purposes. So let me give you one example of why you might care about this kind of thing, despite it not being on the standard kind of computer science list of things you should know about data science. Well, here's a question. Friends of Nine is known to ask, what would you say if you saw this in another country? That is to say, Americans do a thing, and then you say, well, what if that was in Venezuela? How would you interpret it? Which is one way to ask, how would your interpretation of where everybody is change were you to change the context? So here's a related question, which is a piece of work I did with Sahil Chinoy when he was still in the New York Times on the question, if the Republicans and Democrats in the US were a European party, where would they land on an ideological scale? There are a lot of tricky things about this question, and we've had a fair amount of discussion over whether this actually makes sense. But on the assumption that it does make sense, then we are asking a spatial question, and we are asking to generate a space of European parties, and then we're asking to project another set of parties into it. We're going to do it on the basis of things they write. In particular, we're going to do it on the basis of the output of effectively a manual topic model. Lots of people have assigned sentences to topics in the Beitzet Bay, which is the research institute down the road, which has a collection of coded manifestos right back to the Second World War in appropriate policy sorts of topics. So we have the space of like topics we could talk about, but the question is, where are all the European parties on it? And the secondary question is, if we were to take American party platforms and translate them into whatever those languages were, where would they land in the party system? Interesting counterfactual. I should also say that Mr. Chinoy went back to graduate school and became an economist shortly after, joined an economics program shortly after I think we did this stuff, and I take no responsibility for that, none at all. So what are we doing here? We're thinking about documents living in a space. Actually, we're also often thinking about words living in a space, and we're going to generate models that are symmetrical for those things. So one thing about so these documents already do live in a space, right? So there's 3,900 words, and that's a vector of 3,900. And we can ask, how distant is it to the next vector along, representing the other document in a 3,900 space? But that's usually not actually the kind of intrinsic dimensionality that we're thinking about here. What we actually think is that all those dimensions of like words we could use, which we could treat as axes, as coordinates, are actually generated by your position in, let's say, a lower dimensional space. So the structure could be topical, but in this case, the structure is, okay, there's maybe a 2 or 3 or a 4 dimensional sort of space. And if you knew what people were there, then the rest of it's noise. So there aren't actually 3,900 ways to vary. There's only kind of left, right, and up, down, and the other way. So we're looking to figure out where things are in that space. And typically, at least in the example, we're going to do some one-dimensional scaling where we want to line everybody up. This is going to be an exploratory method, so we're still going to have to ask ourselves, like, what is this line that they're lined up on? But we're sort of reading in a different structure. And we'll do a two-dimensional one too. So we can think about, so our assertion here is quite a lot simpler than the STM. It's that if you were to know a position for a document, let's call it theta, there's only one per document. All of those words are expressing the same position. And if you were to know the position of the words within it, let's have beta as being positions of a word in the same space, then these together would tell you how often you see these words at whatever rate. and that and the spatial structure is the thing that matters. And if we think we live in if you want like 3-dimensional thing, you set k to 3, and then you'll have like 3 lots of thetas and 3 lots of betas, which will tell you where each of these words and where each of these documents are in each of the dimensions of space, which is kind of cool. Even if you kind of don't like this, or you don't care about ideological stuff, which this is very naturally built for, then it's a really nice way to visualize contingency tables of the kind that the document feature matrix is. So the first thing we should do is we can actually build one of these things from scratch. So let's take some word data here. Here's a bunch of German manifestos and the words that they have in them from way back in 2002, so that none of the local Germans would yell at me. The FDP is a party, CDU is a party, somewhat rightish, SPD somewhat leftish, PDS somewhat even more leftish, and Greens. Die Grünen are green. And they can say things like Wirtschaftssoziale or Förderung. For our purposes, we'll be interested in Wirtschaftssoziale, so business and social. Let's have it like that. And we might get presented with one of these. That's a document feature matrix, fairly straightforward. FDP says Wirtschaft 14 times. Okay, cool. We're going to make an assumption. What's our assumption? Our assumption is that it's not interesting that the FDP manifesto is long. So it could be short, could be long. That wouldn't really have anything to do with its position on anything. We're also going to make the assumption that Wirtschaft as a word could be frequent, could be infrequent. That wouldn't have anything to do with its position either. If that's true, then we have some implications. And what actually we can conclude from this is that the table margins here, if we think about the margins of this thing, they're uninformative. So position is not about how long you talk. Okay, so all we've got left is like basically what I'm going to call association structure. So it's the fact, for example, that the CDU says Wirtschaft more than Soziale. There's 11 to 8 in that count. So that's basically 1.38. There's a how much do you love business more than social? Yeah, kind of a bit actually. FDP loves it more, so that's 14 to 4, so much more Wirtschaft than Soziale there. And then our comparison is just how much more does the FDP love business than the CDU loves business? And that's a little fact. It's an odds ratio. There's loads of these little facts, and they're all in that table, and none of them depend on marginal frequencies and things like that. So you can make everything more frequent or less frequent. You could like cut the manifestos in half, and you still get the same thing. So that's kind of the basic fact that we want to express, and we want to be able to represent. And we're just going to say, look, spatialize that. Like, give me a spatial model of all of those. How much more I talk about this than that. So relative proportional emphasis is going to be the key here. Okay. So I guess it's worth noting that every model that we've looked at has an opinion about how those associations work. So we could, in fact, have induced topic structure into those associations. Would have made a slightly weird looking model, but that's the information source. Right now, we're just going to say, kind of find me the line, or find me the space that all that stuff lives in, and then project all of these manifestos into it, and also all of the words. Great, let's do it. Let's start with it. We can do it right from the beginning. There's a rate at which you generate, let's say, Wirtschaft. Cool. Let's say it's Poisson. That would be our normal assumption. We can open a textbook and discover that there are two natural models of this tabular structure, which we might summarize as the boring model and the pointless model. The boring model says, here's a parameter associated with how long it is, and here's a parameter that says how often Wirtschaft turns up. And we see Wirtschaft in the FDP exactly as much as we'd expect by chance. It's kind of boring and also uninteresting and unspatial. And then here's the pointless model, which says, yeah, we see it exactly that much, but here's another matrix which adds it up to exactly the right answer, which means that we see it exactly as often as we see it. So that's kind of pointless because it gives us no analysis. What we're looking for is a class of models in between these. So ones that say, yeah, it's like people use these things differentially, like there really is positioning going on. But it's not as complicated as it looks. Actually, everybody lives in a space. So we're going to decompose this guy spatially. And then we're going to get a scaling model, which is actually very nice. Okay. Those are For those of you who were appalled by my description, that's actually the independence model and the saturated model. Okay. So if you, so for intuition here, what we're going to do is take that matrix of everything that wasn't the margins, call it lambda, and do an orthogonal decomposition of it. This is going to be a singular value decomposition. If you haven't met singular value decompositions, think of it as a principal component thing. If you haven't met principal component things, well done you. There's time. The way to think about this is we can rearrange the structure of that matrix so that it has orthogonal columns. That won't be true in general of the words, for example. They won't in any sense be orthogonal to each other. But we can rearrange them that way, and we can order them, ones that are most important for making the data come out, and ones that are least important as we go from left to right. And then if we're feeling very approximate, then our decomposition will allow us to take just one column out of the thetas and one column out of the B there, and say that's our best like spatial linear approximation on a line to lambda there. So that's a rank 1 approximation. For our purposes, theta is a document position, beta is a word position. I'm just going to assert that that's what they are. And then there's a weight that tells us how much is going on. It's going to matter more for more dimensional stuff. And we're going to get this model here. This is an association model invented by Goodman, but actually not really, invented by Hirschfeld, like way back when, persistently reinvented. It's a really good idea. Question, why is that a really good idea? This was way too much algebra. Let's see like why, what are we actually assuming when we do this crazy linear algebraic decomposition? Well, first thing, what we're really going to assume is this. This is what we might call spatial talking. So here's a picture. All of these parties live on a line somewhere. Let's just assume it. And they have positions on a line. There they are, pointing up to the bottom. And all the words in our vocabulary also have positions on this line. There's Wirtschaft just there. And some of them are nearer than others. So now, how would you decide what to say if you were the FDP? And so we're going to write this model and then show that it turns out to be the other model. So there's the position of the FDP, PFDP. And the idea here is you as the FDP want to express yourself being just there. And so you use words that are close to you. And Wirtschaft's pretty close, so you might say Wirtschaft a lot. But Sozial's way over on the other side, and you probably don't say that much. And you say it decreasing with distance. So this is a quadratic utility kind of model. If we write that down, we get the top line of the equation underneath. So there's a squared term there. It makes it all symmetrical. Doesn't matter like left or right. It just has to be near on this line. But if we kind of rearrange it a little bit, then we end up right at the bottom with something that looks exactly like our association model. And the bottom line here to take away is that you are assuming the thing on the top when you fit the model on the bottom. So we're assuming spatial talking in the same way as you might assume spatial voting or any other kind of spatial analysis that you would get in like microeconomics or voting studies or stuff like that. So yeah, some familiar stuff. Conversely, if you want to make it even closer to looking like voting, then let's say there are only two things you can say. You can say Sozial or you can say Wirtschaft, and that's just the entire German political vocabulary. Then you're all these parties. If we condition on the amount you say, then we can have a model of essentially a little logistic regression down there, which says if I am where I am, I'm the SDP, FDP, the SPD, for example. Then here's the story about like how much of these things I should say. So what's the balance of Sozial and Wirtschaft? And these are related. So the point is, it's spatial talking. Cool. That's actually kind of nice. It's not a crazy way to think about position taking. So I'm really not going to. So what I'm not going to do is borrow somebody else's vocabulary and say not that, because I want to say things that are like near to me. And he would say that, but I would say not. That's not going to fly. We need separate things. Okay. The interesting special case of this is where there's actually really are only two things you could say. And you might say, well, that's kind of nuts. How would you do? When would that be true? And the answer is it's true when you're being a little bit more discriminative. So if you have a bunch of vocabulary that you think is right, then you can bundle them all together as one sort of token, and then that's a count. And then there's a count of some lefty stuff as well. And you'll end up with a measure a bit like this, which is a log ratio of things. So we've seen lots of log ratios before, and here's another one. And this is the 2D case of the model that I just showed you. So if you want to expand this out and not assume that you want to decompose those counts, that's the model you want, which will fit. Okay. Yeah. So one of the things that we should ask ourselves immediately with this is it's going to put documents and words in a space. So it better make sense that there's a space, because whether or not there are in fact in some real sense dimensions, then everything's going to end up on one, and we're also going to have to interpret what they are. So typically, because of that spatial talking picture, if we want to know what the vocabulary is, then we're going to look at the extremes of the betas, the very high ones and the very low ones, because those are going to tell you essentially what the definition of the dimension we've got is. And that's going to be exploratory, interpretive, shall we say. If we happen to know those things, or we have a set vocabulary or a set of categories, then it's going to be easy. But yeah, that happens less often. The tricky case here is when we have to decide whether we really want to see positions at all. So sentiment's kind of a position, right? It's like somewhere between the positive and the negative, or the indifferent in the middle. That could be thought of as a dimension. Things like Euroscepticism might be a dimension, or maybe it only goes one way. Populism, unclear. Right? So yeah, so there's a substantive story that you have to tell about why you would want to make sense of this thing. But when you do, you do. So let's. One of the downsides of fitting one of these models is, as I said, it's going to find you a dimension. So here, courtesy of Ken Benoit, is this model going appallingly wrong? So what you're looking at here is a whole bunch, in fact, all at the time of the budget debates in Ireland. Now, in theory, the budget, when the budget comes out, it will reflect the ideological preferences of the government of the time. And it will talk about a bunch of stuff that's in the budget. But one thing you notice here is that it looks, if you were to just pull out one dimension, then that one dimension lines up perfectly with time. And it doesn't line up perfectly with the sort of left-right thing that you were expecting. So you can be surprised by what the dominant association direction is. Question: why does that happen? Answer: the budgets talk about a lot of things, and the things that you spend money on in 1923 are not the things that you spend money on in 1975, and probably not the things that you spend money on in 2004. So the vocabulary is so slowly moving into the future, where we buy more things and spend on more things, and that dwarfs the little drift of left and right of the governments that you see separately off the line. So here's an exploratory case where, yeah, it hasn't actually got what you want. Flip this around. If you're an archaeologist, then you use these kinds of models for exactly this purpose. That's actually a well-working model for an archaeologist, where the kinds of shards of pots that you see move smoothly in time, and therefore you like to infer time and date them. So that's kind of cool. But here, not so useful, always worth plotting. Point here is that we're going to find a dimension and we're going to figure out what it is. So there it is. Okay. The natural thing, and I'm going to end here and do a little practical things, is can we do this in 2 dimensions? And the answer is yes, we can do this in 2 dimensions. And all we're doing is like adding, we had a rank 1 approximation before, and now we'll just like add another dimension. We know that it's going to be orthogonal and we can't have it any other way. So this is not factor analysis. We can only orthogonally rotate. That's it. Just because we count data. But we can add one, and if we do, then, and we do it, let's say, to the German parties here, then we get these nice biplot things. So what is a biplot thing? This is a biplot, and it's bi both because there's 2 dimensions in it, but more importantly, the topics that have been manually coded in the case of this data, and the documents they've been coded from are in the same space, in some sense. And they've been plotted here in black and gray. So the utility of that kind of diagram is that it kind of tells you who talks about what. We're officially over time, says someone in the audience. Yes, it's true. Yeah, I will definitely be done by 2:45. That is certainly true. Or I will simply stop. This is in fact my last slide, so we can run a quick analysis, and then everyone can go home. That work? Yeah, let's try that. Okay. Yeah, so how do we read this thing? Just quickly. If you were a party and you were just here in the middle, then you use all of these topics at about the rate we'd expect you to. That would make you a very boring party. If you parties that use similar bundles of topics bundle together. So here's the FTP talking about the same sorts of things. Question, what did the FTP talk about? Well, if we draw a line to the FTP from the center here and then to, for example, this one here, constitutionalism positive, being friendly about constitutions, then you'll find the angle between them is very narrow. And the way to interpret that is that's what the FTP talks about. So similarity of direction at 90 degrees. Traditional morality, the FTP is indifferent to at 90 degrees. And there's political authority just here. It's at 180 degrees from it. And yeah, it kind of doesn't really talk about that. So relative emphasis, not much of the latter. Cool. And yeah, that's a biplot, useful thing. Let's do this practically. In the meantime, you should perhaps drop a question in if you want one, if you haven't all run away. Good. Let's do the same thing. Right. Into paragraphs because the scaling model doesn't really care about topics, so that's cool. Let's give it a shorter name because I'm lazy, and deal with the stop words and make a DFM. Those are all exactly the same steps as we did last time, and then fit a model, and then interpret it, and we'll be done. We're going to do a one-dimensional thing here. You can worry about the multi-dimensional things later. Point to note here, there's our document feature matrix. That's all we need. All I'm doing here is asking that the person, because there's an identification ambiguity here, because it doesn't know anything about substantive left-right, we're asking whether we would ask whatever the theta the position associated with the third speaker, make it to the left of the 21st speaker. That's just to kind of fix our direction. It's not actually substantive information at all. So we can, from this model, we can look at our coefficients. We can look at those betas. Those are the positions and the features. But right now, let's just see what it says. So what we're actually interested in is where would these speakers be if this were a reasonable way to think about them. So we'll pull the predictions out and we'll get some confidence intervals because confidence intervals are good. Gosh, they look like that. So there's a estimated position for Allard. And just gonna, yeah, okay. So that's sorted from left to right. And the very last thing I'm going to do is actually make the plot. And we will this question. Right. Okay. So let's stare at this just for a few moments. So there's an estimated position. This has no scale. This is essentially mean zero, variance 1 because it's an abstract space. I've colored this according to party affiliation. So these are the Democrats and those are the Republicans in red, and there's a lone Democrat in the middle. But none of that was used in this model. It's fairly certain of the extremes, but not very certain. In particular, it's not very certain about Reed, presumably because he didn't say very much. And there's also an extremist over here who we investigate a bit further in more of these exercises. So we'll see like exactly why that guy's out there. But I guess one natural thing to take away is that substantively that looks kind of reasonable. So these are the people you would expect to be talking about things on the right, and these are the people you would expect to be talking about things on the left and on the right. And the next step, which we won't do, would be to look at these betas and say, okay, what are they talking about? So what are the words that put you this side rather than that side of the scale? But that I think that has to wait for another time. Or indeed, it has to wait for you to take my code home and go play with the rest of it. So let's say that's that. I will, at this point, I think I've run through a bunch of tools that you may find useful for treating text as data. They are certainly not exhaustive, but they may be useful to you. Try to bring out some of the considerations if you actually apply them. And yeah, then I hope that was in some way illuminating. And I shall drop the slides up there in a moment. So all I have to do now is answer questions until Olga switches me off, which I'm very welcome to do. Question. Overall, the first part, part 2, document classification. Yeah, document classification. So my recommendations may be a little old at this point, but I seem to remember Manning and Schutzer having a nice, having 2 nice books actually that cover overlapping sections of this, including much of the material on classification. So that should be, I think it's called Statistical Natural Language Processing. But there may be better ones, but that's a good one. Yeah, I think that will probably cover most of what we want. I should also note, as by way of advertisement, that let's see, Grimmer, Stewart, and third author's eluding me, the author of the STM, Roberts.
Roberts.
Thank you. Shame on me. Have a book just about to come out in Princeton University Press, I think, not actually ready to buy yet, but like, I guess, in press, which is a nice, which ought to be a very nice monograph on text analysis quite generally, and we'll cover this sort of material plus a vast amount of other stuff in more sophistication than I've been able to get into here. But that has very good, at least if the version I read is still that version, that has amazing stuff in it. So I'm going to recommend that. Really, actually, sight unseen. That's a great book. That's going to be a great book on text analysis, I believe. Right. So question, when we construct our textual data in corpus, how can we create variables other than the text? Great question. Those are going to be the document variables, and you can simply assign those in. So you have your corpus, it's called corp. And if you happen to have a variable which is exactly the length of the number of documents you've got in that corpus, then you can say corp $, name of my new variable, and then simply assign your new stuff in, and that will become part of the document variables. Yeah, that's a very standard, useful thing to be able to do. Also, my apologies for going on and on and on, but you know, old dudes, what can you do? Conquered the YouTubes. Excellent. Well, folks, thanks for all the great questions and your indulgence, and I hope you have fun with more of this stuff.